More than 440 million years ago, Earth is an ocean-dominated planet with most life living beneath shallow seas that spread across wide continental shelves. Then the climate swings hard, sea levels fall, habitats collapse, and the world enters the first great mass extinction in the fossil record. In the long silence that follows, survival is not just about endurance. It is about rebuilding ecosystems from the ground up as reefs, food webs, and new kinds of marine life slowly return. If you enjoy quiet journeys into deep time, please like, subscribe, and share. Thank you for watching. Now let's begin. In the long aftermath of the end Ordovician extinction, Earth turns slowly under a sky that is clear but thin and cold. Great ice sheets still spread across the high latitudes of the southern supercontinent Gondwana, stacked in layers that reach from the interior of the landmass toward the continental margins. This world sits near the end of a long interval of global cooling known as the Hernantian glaciation, when average temperatures fall well below those of earlier Ordovician time, and large parts of the planet lie under persistent snow and ice. Sunlight still reaches the surface, but a high fraction of it reflects from bright ice, and the planet as a whole stores less heat. The air above the ice sheets remains dry and dense, and winds move from the frozen interior toward the coasts, where they pick up moisture from the remaining open water and return it to land as snow. Storm systems track along the edges of the ice, where the contrast between cold land and somewhat milder ocean air is strongest, and they maintain the ice caps by feeding them with new frozen precipitation year after year. Sea level stays unusually low because so much water is locked up as solid ice on land. Broad areas of former seafloor along the margins of continents stand exposed as cold, barren plains, etched by channels cut from meltwater in the short, warmer seasons, and then frozen again. The outlines of the continents differ from those of earlier times, not because plates move quickly, but because the shoreline itself has shifted downward. What had once been shallow epicontinental seas, which are shallow seas that lie on top of continental crust, are now drained or greatly reduced, leaving behind patchy basins where water still pools. The remaining oceans occupy deeper basins and show a sharper division between the frigid high latitude waters and the somewhat warmer equatorial belt. Island chains and volcanic arcs rise from the oceans, but they too are affected, with many lower slopes now standing above water, newly exposed to cold air and frost-driven weathering. The global carbon cycle, which is the slow exchange of carbon between rocks, oceans, atmosphere and life, operates now in a climate that favours continued cooling. Chemical weathering of exposed continental rocks proceeds even under cold conditions, as liquid water from seasonal melting seeps into fractures, freezes and breaks the rock apart. This process removes carbon dioxide from the atmosphere over long timescales, as dissolved ions wash into the ocean and help form carbonate minerals that lock up carbon in sediments. The continued drawdown of greenhouse gases helps to keep the climate cool, even as orbital patterns and volcanic emissions apply their own gentle changes. The atmosphere carries less water vapour overall than during warmer intervals, which further reduces its ability to trap heat, reinforcing the cold state. High above, the circulation of air in Great Cell still transports energy from equator to pole, but the temperature contrast between low and high latitudes is strong, so jet streams are tight and storm paths focused. On land, complex plant cover is still absent. Only simple microbial crusts and perhaps small low-lying patches of early non-vascular plants occupy some moist niches near coasts and river mouths. Large areas remain bare rock, gravel or thin soil scoured by glaciers in some regions and by persistent frost in others. The lack of deep-rooted vegetation means that when meltwater flows it readily carries loose sediment toward the sea building, out small deltas on the now exposed shelves, or filling in low-lying basins. Dust from the glacial outwash plains and from ground rock can be carried by wind over long distances, adding a fine haze to the atmosphere during dry periods. These particles influence how sunlight is scattered and absorbed, but in this cold world their effect is modest compared to that of the extensive ice cover. The cryosphere, which is the part of the Earth system that includes all forms of ice and snow, dominates the visual and physical character of the globe. At high latitudes, ice sheets are thick and slow-moving, deforming under their own weight and creeping outward over many thousands of years. Along their margins, outlet glaciers slide toward lower ground, where they may terminate in the sea as tidewater glaciers that carve off floating icebergs. The presence of such ice streams carves deep troughs into the underlying rock and directs meltwater into specific channels. At slightly lower latitudes or lower elevations, seasonal snowpacks accumulate and partially melt each year, sending pulses of cold, mineral-rich water into rivers and marginal seas. Each melt season is short, and the return of winter quickly restores snow cover, so the net balance remains in favour of ice retention, rather than rapid loss. In the equatorial belt, conditions are less extreme but still cooler than in much of earlier Ordovician time. Warm shallow seas have shrunk, and the remaining low-latitude waters can be cooler at the surface because of changes in currents and the influence of the global ice volume. Tropical storms may still form over the open ocean, but the distribution of heat that powers them is altered, and their tracks are guided by a different arrangement of continents and sea. The atmosphere here holds more moisture than at the poles, and heavy rains fall on coastal regions during certain parts of the year, yet the hydrologic cycle overall is muted compared with that of a warmer Earth. Rivers draining toward the sea carry the legacy of the glacial world upstream, moving fine rock flour and sand eroded from ice-covered highlands into the marginal ocean basins. The legacy of the mass extinction is present but not visible from orbit. Many marine groups that had flourished in the earlier Ordovician seas have already passed through their crisis with large fractions of their former diversity lost. What remains of complex life persists mainly in the oceans, which still cover most of Earth's surface, but from the large-scale climate perspective, the planet appears more like a colder version of itself than a completely alien world. Ice caps gleam at one end of the globe, darker ocean basins fill the low areas, and irregular continents lie between, bounded by a shoreline that has shifted, but still traces familiar patterns of rifted margins and mountain belts. Over timescales of hundreds of thousands to a few million years, the balance between ice accumulation and ice loss will gradually change, but in this snapshot of the recovery interval, the cold state continues to frame the possibilities for life in the oceans and along the flooded and exposed edges of the continents. Over long stretches of Silurian time, the cold grip of the ice sheet starts to loosen, not with a sudden shift, but with small changes that add together across many seasonal cycles. Volcanic centers on land and beneath the oceans continue to release carbon dioxide into the atmosphere, and as some formerly exposed rock surfaces become recovered by soil or water, chemical weathering no longer removes greenhouse gases at the same rate as during the peak of glaciation. The balance in the carbon cycle tilts slowly toward a higher concentration of greenhouse gases, and the atmosphere begins to retain a little more heat. Orbital patterns which control how sunlight is distributed between seasons and latitudes move through their own cycles, and some of these states favor milder winters and slightly warmer summers at critical latitudes where the great ice sheets sit. In the early phases, the change is subtle. Summers at the edges of the Gondwanan ice masses bring longer periods above freezing, and meltwater streams flow for more weeks each year across the glacial forelands. The surface of the ice becomes pitted with melt ponds and intersected by channels where liquid water cuts down into the upper layers, darkening areas that had once been bright and reflective. Each dark patch absorbs more sunlight than the surrounding snow warms more quickly, and expands a small positive feedback that helps local melting to progress. At first, winter cold easily restores the snowpack and spreads fresh white cover across the surface, but over thousands of years the cumulative effect of longer, warmer melt seasons becomes clear in the gradual thinning of the ice margins. As ice retreats from some coastal sections, the weight on the underlying crust decreases, and the land surface begins to respond by slowly rising a process known as isostatic adjustment. At the same time, the total volume of water stored as ice on land declines, and global sea level begins to rise. The interaction of these two processes means that the relative level of the sea along any given stretch of coastline depends on both the global signal of meltwater added to the oceans and the local response of the crust to the loss of ice. In some places, the land lifts faster than the sea rises, and former marine areas remain exposed a little longer. In many other regions, the global sea level rise outpaces uplift, and the shoreline moves steadily landward. Broad continental shelves that had been dry ground during the glacial maximum now experience a slow, persistent marine transgression, which is the landward shift of the shoreline as the sea floods new territory. River valleys carved into the exposed shelf during low sea level stand, ready-made to receive the returning ocean, and as sea level rises they become flooded, forming long inlets and shallow embayments that trace the former courses of rivers. Low coastal plains sink beneath advancing shallow seas and become the floors of new epicontinental seas. Over spans of hundreds of thousands of years, the map of shallow water around each continent redraws itself. On Gondwana, where ice had advanced far toward what are now temperate latitudes, the retreat of ice margins opens wide tracts of ground that had been buried for long intervals. Meltwater lakes occupy some depressions at the ice front, while in others the sea moves in directly as the ice margin withdraws below sea level. On other landmasses such as Laurentia and Baltica, which sit closer to equatorial or mid-latitudes, the signal of sea level rise is expressed in the drowning of coastal lowlands and the re-establishment or broadening of shallow interior seaways. The arrangement of smaller terrains and island arcs also matters. Chains of islands that had stood as continuous barriers at low sea level become cut by new straits as sea level climbs, allowing surface waters and drifting ice to move more freely between previously separated basins. In some regions, narrow seaways widen into broad channels, altering the paths along which tides and long-distance currents can flow. Storm systems respond to the reorganized pattern of ocean and land. As sea ice cover in some high-latitude marine areas becomes seasonal, rather than permanent, open water can interact directly with cold overlying air in autumn and early winter, producing bands of cloud and snowfall that feed the remaining ice sheets, but no longer sustain their former size. The contrast between the still cold interior of Gondwana and the somewhat warmer surrounding seas persists, but with rising global sea level and a slow increase in average temperature, the strength and seasonal timing of that contrast change. This modifies the tracks of low-pressure systems and the typical positions of storm belts. In the equatorial belt, the expansion of shallow seas over previously exposed shelves increases the area from which water can evaporate and later return as rainfall. The hydrologic cycle muted during the coldest glacial stages gains energy as more of the planet's surface participates in evaporation and precipitation. However, the change remains gradual when viewed over geological timescales, and each individual year still resembles its neighbours closely. To an observer on the ground at any one time, the coastline might seem stable, even as the long-term average trends toward flooding. As sea level continues to creep upward, the pattern of sediment delivery from land to sea shifts. Rivers that once cut directly across exposed shelves to reach the glacially lowered shoreline shorten as their mouths are drowned. Sediment begins to accumulate closer to the original continental margin, and new deltas prograde into the slowly deepening waters of the newly formed embayments. Farther offshore areas that had been subject to subaerial erosion now lie under a thin layer of seawater and receive only fine sediment delivered by suspension and gentle bottom currents. The reflooding of shelves also modifies the thermal inertia of the coastal zone. Water has a higher capacity to store heat than rock or soil, so shorelines fringed by shallow seas experience less extreme swings in temperature over the year than those bordering exposed shelves under cold air. This moderates the seasonality of some coastal climates and slightly alters the strength of land sea breezes that control how air masses move inland. From a global perspective, the total sea level rise across the full deglaciation is large, but the rate at any given moment remains slow on human timescales. Across millions of years, however, even small average rates accumulate to hundreds of meters of vertical change, enough to re-establish extensive epicontinental seas in many regions where they had once been drained. The geography of shallow marine space that had supported rich Ordovician communities begins to return in outline, even though the biological cast that will later occupy these spaces has been thinned and rearranged by the extinction pulses. The outer framework that will guide the next stages of environmental and ecological recovery is thus reset by the combined effects of ice sheet retreat, global sea level rise, and the interplay between crustal uplift and subsidence along the continental margins. The planet moves from a state dominated by exposed glacial plains and low sea level toward one in which shallow seas once again encroach over the edges of continents ready to host the next phases of change in the oceans that cover most of Earth's surface. In the early Silurian world that follows the end Ordovician crisis, the broad arrangement of continents and oceans sets the outer frame within which recovery takes place. The southern supercontinent Gondwana still dominates one hemisphere, its bulk stretching from polar to temperate latitudes, while smaller continents such as Laurentia Baltica and Avalonia occupy positions closer to the equator and mid-latitudes. These land masses are not fixed, but on human timescales their motion is too slow to notice. What matters for the recovering planet is how their current shapes and relative positions control the pattern of ocean basins, narrow seas and broad open waters. With sea level rising as ice retreats from Gondwana, low-lying coastal regions and interior depressions along its margins are increasingly flooded. Shallow seaways begin to penetrate into areas that had been part of the glacial foreland, creating long, narrow marine corridors fringed by gently sloping shelves. Around Laurentia and Baltica, the same global rise in sea level re-establishes or enlarges epicontinental seas that had been drained during the glacial maximum, turning former river valleys and low plains back into submerged platforms. The Iapetus Ocean, which had separated several of these land masses earlier in the Paleozoic, is in the process of closing as converging plates carry island arcs and microcontinents toward the larger continental blocks. Subduction zones along these convergent margins generate volcanic arcs and deep ocean trenches, adding further complexity to the seafloor topography and introducing chains of islands that can redirect surface currents and wind patterns. At the same time, other oceanic domains remain wide and open, spanning great distances between continental margins and allowing large-scale circulation cells to develop. The shapes of continental outlines with their embayments, promontories, and attached microcontinents influence how the rising seas spread. In some regions, sea level rise converts broad coastal plains into wide, shallow shelves that extend hundreds of kilometers from the new shoreline before dropping into deeper water. In others, steep continental margins mean that even substantial flooding only produces narrow bands of shallow sea before the seafloor plunges into the depths. Island arcs formed above subduction zones where oceanic plates sink into the mantle create strings of emergent land that separate marginal basins from the open ocean. Between the islands, straits of varying depth control, whether water exchange is mostly at the surface or includes deeper layers, setting up a pattern of partial connection that is sensitive to relatively small changes in sea level. Spreading ridges where new oceanic crust is formed rise as long topographic swells on the seafloor, and can locally shoal water depths, further structuring the pathways along which currents flow. As ice thins on Gondwana and sea level continues its slow upward trend, some marine embayments that have been isolated during low sea level become connected to larger ocean basins through newly opened straits. These changes create new ocean gateways, which are regions where water masses move between major basins or between open ocean and interior seas. Even modest gateways can exert a strong influence on circulation because they determine which waters can enter or leave a basin and at what depths. For example, a shallow sill at the entrance to a shelf sea allows surface waters and perhaps part of the upper thermocline to exchange with the open ocean, while deeper waters remain more isolated and can evolve different temperature and oxygen conditions. In contrast, a deeper connection permits more complete renewal of the water column. Across the recovering planet, numerous such sills and channels exist, and their evolving depths as sea level rises shape the pattern of connectivity. On the scale of whole ocean basins, the distribution of continents influences where warm and cold water can move. Equatorial continents such as Laurentia, with broad shallow seas extending into low latitudes, can intercept and redirect warm surface currents that would otherwise flow more directly around the globe. The presence of land at certain latitudes can also block or divert zonal flows, forcing water to move poleward or equatorward along the edges of continents instead. Around Gondwana, high latitude positions mean that its margins interact with both cold polar waters and more temperate water masses, and the arrangement of its coastal outline influences how these water types mix or remain separate as they circulate along the margin. The closing of the Apatus Ocean and the associated deformation belts build mountain ranges along some continental edges. These new or growing highlands alter regional patterns of wind and precipitation, and change the delivery of sediment and dissolved materials to adjacent seas. In the rain shadows behind mountain belts, climates may become drier, while windward slopes receive more precipitation and support more intense chemical weathering. The rivers draining these highlands carry their loads into nearby ocean basins, building deltas and submarine fans that record both tectonic uplift and climatic conditions. Thus, the evolving geography of converging plates not only changes the physical shape of ocean basins, but also feeds back into the long-term carbon and nutrient cycles that affect climate and ocean chemistry. Smaller terrains and microcontinents add further detail to this global map. Some are in the process of docking with larger continents, forming new continental margins and closing off parts of former ocean basins. Others drift within broad oceans, carrying their own narrow shelves and small interior basins. As sea level rises, even these relatively small pieces of crust can host shallow marine environments that are important regionally because they offer hard rock substrates, varied topography, and local variations in climate and runoff. Chains of volcanic seamounts, some of which rise to near sea level, dot the floors of major oceans, and may occasionally break the surface as islands, though their role at this time is mostly as submerged obstacles that affect flow and sediment distribution. Over tens of millions of years, the slow drift of continents continues to reshape connections between basins, but within the recovery interval following the end Ordovician extinction, the most important changes are the progressive flooding of shelves and lowlands and the opening and deepening of critical seaways. In this adjusted configuration, broad shallow seas wrap around the flanks of Gondwana, spread across parts of Laurentia and Baltica, and nestle between island arcs and continental promontories. Deep ocean basins occupy the spaces between the major land masses, linked to one another by a network of gateways whose dimensions change only gradually but significantly. The interplay between this geography and the slowly shifting climate will determine how heat and salt are moved through the world ocean, where surface waters can sink to form deep currents, and where isolated pockets of water may become stagnant. These are the large-scale controls that will frame the conditions in the ocean itself and shape the spaces into which recovering marine life can eventually spread, even though at this outer level of description, the focus remains on continents' basins and the corridors of water that lie between them rather than on the details of the water masses they contain. In the recovering oceans of the early Silurian, temperature once again becomes a primary organizer of water masses from the surface to the deep basins. The Endordovian glaciation has left a legacy of cold deep waters and strong contrasts between high latitude and low latitude regions. But as ice retreats and sea level rises, the pattern of heating and cooling at the ocean surface shifts. Sunlight falls most directly on the equatorial belt, where newly expanded shallow seas and broad open waters absorb energy through much of the year. At higher latitudes, especially around the margins of Gondwana, seasonal changes remain pronounced, with winters that still support sea ice in some coastal regions, and summers that now bring longer periods of open water. This seasonal alternation of freezing and thawing acts on the uppermost layer of the ocean, setting up a surface zone that is more variable in temperature than the deeper waters below. In many regions, the upper tens of meters of the ocean form a mixed layer that is stirred by wind and waves. Within this layer, temperature and salinity are relatively uniform at any one time, because physical mixing continually blends new inputs of heat, cold or fresh water from rain, and river runoff into a common mass. Below the mixed layer, water becomes more stable and less affected by short-term weather, and a vertical gradient in temperature develops. This zone of rapid change with depth is known as the thermocline. Its exact depth and strength vary from place to place. In warm, stratified tropical regions it can be quite sharp and shallow, while in cooler, higher latitude waters it may be weak or almost absent during seasons of intense mixing. Beneath the thermocline, if it is present, lie the deep waters which retain their cold temperatures over long time scales and interact only slowly with the surface. The distribution of temperature in the recovering ocean is closely linked to the geography of basins and the position of continents. In broad equatorial seas over the flooded shelves of Laurentia and Baltica, solar heating of the surface produces warm, low-density surface waters that tend to remain above cooler underlying layers. Wind-driven mixing can deepen the warm surface layer during storms, but in calm periods the upper ocean stratifies again with a distinct warm lens overlying cooler water. The presence of shallow seafloors in these regions means that the entire water column can still be influenced by seasonal changes if depths are modest, yet even here a tendency toward layered structure appears as the climate warms. In contrast, along the high latitude margins of Gondwana, where surface cooling and sea ice formation are still important in winter, the surface waters can become denser than the waters below them when they cool, and in some places when salt is released from growing sea ice. These dense surface waters may sink and spill down continental slopes into deeper basins, carrying cold temperatures into the ocean interior and helping to renew the deep water masses. This process, known broadly as deep water formation, does not need to be concentrated in a single location. Rather, it can occur in a patchwork along various cold margins and shelf breaks depending on the detailed interplay of cooling sea ice and salinity. Narrow seaways and semi-enclosed basins add further complexity. Where shallow sills restrict deep connections to the open ocean, temperature structures may become more stratified because only the upper layers are able to exchange freely. Surface waters warm and cool with the seasons, but the deeper portions remain closer to a long-term average, shielded from rapid changes above. In some such basins, strong seasonal heating of the surface followed by cooling can lead to the formation of internal layers that persist through much of the year, with only occasional mixing events invigorated by storms or by changes in wind direction. Where basins have deeper connections, the temperature of the water column is set more by the properties of the water masses that flow in and out along different depth levels. Warm surface waters may enter from adjacent open oceans, while cooler intermediate waters and cold deep waters either fill from nearby source regions or remain in place from earlier periods of circulation. Surface currents redistribute heat horizontally. Driven by the prevailing winds and guided by the shapes of continents and island arcs, they carry warm water away from low-latitude heating zones and return cooler water toward the equator. Around equatorial continents, currents can split and follow the margins northward and southward, bringing warmth into higher latitudes and moderating temperature contrasts. Where winds blow persistently parallel to a coastline, they can cause surface waters to move away from the shore, drawing up cooler waters from below in a process known as coastal upwelling. In the recovering Silurian oceans, such upwelling zones likely develop along some continental margins, and the leeward sides of island arcs, creating narrow bands where cooler subsurface water reaches the surface even at relatively low latitudes. These bands represent local exceptions to the general pattern of warm surface conditions in the tropics, and they have implications for nutrient supply and biological productivity that remain tied to the physical temperature structure. The vertical pattern of temperature is not static. Over timescales of years to decades, changes in wind strength, storm frequency, and seasonal ice extent alter the depth of the mixed layer and the sharpness of the thermocline. Over the longer spans of the early Silurian recovery, as the climate shifts away from its glacial extreme, average sea surface temperatures increase slightly, especially at mid and high latitudes. This tends to strengthen stratification in some regions, as the difference between warm surface waters and cool deep waters grows. However, because the legacy of the glaciation includes relatively cold deep waters stored in the basins, the response is uneven. In certain high-latitude shelf, seas continued strong winter cooling and periodic sea ice formation keep the water column more thoroughly mixed, delaying the establishment of a permanently strong thermocline. Thus, at any given time, some parts of the world ocean show stable layered temperature profiles, while others remain seasonally or persistently mixed from surface to depth. The slow relaxation of the ocean from its glacial state also affects how quickly deep waters respond to surface warming. The deep ocean has a large capacity to store cold, and the renewal of its waters through sinking at high latitudes is limited by the rate at which dense water forms and descends. Even as surface waters warm modestly in response to increased greenhouse gases and changing insulation, the deep basins lag behind retaining conditions set by the colder climate in which their waters were last formed. It takes many thousands of years for a full turnover of deep waters to occur, and during much of the recovery interval, the ocean interior remains cooler than it will be later in the Silurian. This vertical temperature contrast plays a role in controlling how other properties transported with the water are distributed with depth, although those properties involve additional processes beyond heat alone. Temperature structure differs between open ocean and epicontinental seas. In wide, shallow interior seas that flood continental interiors, the entire water column may lie within the zone that exchanges heat with the atmosphere over a year. These seas can warm substantially in summer and cool strongly in winter, leading to large seasonal swings in temperature from surface to sea floor. Their shallow depths make them sensitive to changes in air temperature and wind, and they can flip between stratified and mixed states over the course of a year. In deeper shelf regions and adjacent slopes where water depths extend beyond the reach of seasonal heating and cooling, the mixed layer rides atop a more stable temperature structure. Here, the upper ocean feels the changing seasons and gradual climate trends, while the deeper portion interacts mainly with slowly moving water masses formed elsewhere. Across all these settings, the recovering Silurian ocean arranges itself into a three-dimensional pattern of temperatures that varies from place to place but obeys certain broad principles. Warm, light water tends to occupy the surface. Cold, dense water tends to sink and fill deeper levels, and the interaction of winds, currents, and basin geometry determines where mixing is strong enough to erase vertical gradients and where stratification can persist. The imprint of the preceding glaciation ensures that cold, deep waters are still common, particularly in basins that receive dense water from cooling high-latitude shelves. Overlying these reservoirs, a surface ocean of gradually moderating temperatures begins to re-establish more stable patterns, setting the physical background against which other aspects of the marine environment will evolve as recovery from the first great mass extinction proceeds. In the recovering oceans, oxygen joins temperature as a key factor that varies from the surface to the deep basins and from one region to another. The end-Ordovician extinction is closely tied to changes in oxygen availability, with evidence for intervals when large parts of the seafloor experienced low oxygen or even nearly oxygen-free conditions. In the early Silurian, as climate and sea level adjust, these patterns do not reset instantly. Instead, oxygen distributions evolve gradually as the balance between physical mixing, biological activity and chemical reactions in the water column shifts. At the surface, in contact with the atmosphere and stirred by waves and wind, seawater is generally well supplied with oxygen. Exchange with the air continually tops up dissolved oxygen in the mixed layer, especially in cooler waters, where the gas is more soluble. Photosynthesis by plankton and other primary producers in the sunlit upper ocean adds more oxygen during daylight hours, as they use sunlight to convert carbon dioxide and water into organic matter. In this zone, short-lived drops in oxygen can occur locally, when respiration and decay temporarily outpace supply, but on average the combination of air-sea exchange and photosynthesis maintains relatively high oxygen levels. Moving downward, oxygen begins to decline where physical mixing weakens and where organic matter sinking from the surface is consumed by microbes and animals. As particles of dead plankton, fecal pellets, and other fragments of organic material leave the mixed layer, they become food for bacteria and small organisms that live in deeper waters. These consumers use oxygen as they respire, breaking down the organic matter and releasing nutrients and carbon dioxide back into the water. If the supply of organic matter is high and the rate of physical renewal of deep water is low, the result can be a broad zone at intermediate depths, where oxygen concentrations are reduced compared with the surface. This kind of oxygen minimum zone is a common feature of many modern oceans, and likely developed in parts of the Silurian Ocean as well, though its exact depth and thickness would have varied with basin structure and circulation. In some regions, particularly along productive continental margins, and in semi-enclosed basins, the balance between oxygen consumption and resupply shifts further toward depletion. Where deep water renewal is sluggish, because sills restrict exchange, or because density contrasts inhibit mixing, the oxygen drawn down by ongoing respiration is not replaced quickly. Over time, oxygen levels in the bottom waters can fall to very low values, or even be exhausted altogether. Sediments deposited under such conditions record the lack of oxygen through their fine laminations, which are undisturbed by burrowing animals that require oxygen to survive. Geochemical signatures in these rocks also indicate that at times, hydrogen sulfide and other reduced chemical species accumulate in the water column, reflecting a switch to microbial processes that do not use oxygen. During the end-Ordovician extinction itself, such anoxic or even euxinic conditions, meaning waters that are both oxygen-poor and sulfide-rich, appear to have become widespread in some deeper basins. In the early Silurian recovery, the extent of these low oxygen zones contracts and expands as climate sea level, and circulation adjust, creating a patchwork of more and less hospitable seafloor environments. Along broad, newly flooded shelves, water depths are often shallow enough that regular mixing by storms and seasonal cooling can bring oxygen-rich surface waters down to the seabed. In these settings, especially at mid and high latitudes where winter cooling is strong, the entire water column may remain well oxygenated for much of the year. Benthic animals that survived the extinction or recolonize from refuges can once again inhabit these bottoms, re-establishing a basic level of biological activity in the sediments. In contrast, on deeper outer shelves and slopes, and in adjacent basins where water is more stratified, the seafloor may continue to lie beneath low oxygen waters for extended periods. The interface between well-oxygenated and poorly oxygenated regions thus often falls along depth gradients and across subtle topographic features reflecting the delicate balance between physical and biological processes. Geography plays a central role in shaping these patterns. Narrow seaways with shallow sills may allow only surface waters to exchange freely between basins, leaving deeper layers relatively isolated. In such basins, if surface productivity is high and large amounts of organic matter fall through the water column, the bottom waters can be prone to oxygen depletion. Conversely, open connections to regions of active deep water formation can help maintain oxygen at depth. Where cold, dense water forms on high-latitude shelves and sinks, it carries with it the oxygen acquired at the surface. As this water spreads along the seafloor into adjacent basins, it can ventilate deep environments and displace older, more oxygen-depleted waters. The strength and pathways of these deep currents depend on details of basin geometry and the prevailing climate, but their presence or absence makes the difference between well-oxygenated deep sea floors and persistent dead zones. River input and runoff from land also influence oxygen patterns indirectly. As ice retreats and vegetation on land slowly expands in favourable regions, weathering and soil formation change the mix of materials delivered to the sea. Nutrients in river waters can stimulate primary production in coastal zones and shelf seas, increasing the amount of organic matter produced at the surface. If this extra production is balanced by efficient grazing and recycling in the upper ocean oxygen, demand at depth may not change dramatically. However, if more organic material escapes the surface food web and sinks deeper, waters may experience greater oxygen consumption. Thus, the same processes that underpin the recovery of primary production after the extinction can under some conditions contribute to low oxygen stresses in particular parts of the ocean interior. Seasonal changes superimpose additional variability. In high-latitude shelf seas, winter cooling and storm mixing tend to increase oxygen levels throughout the water column by bringing surface waters into contact with deeper layers. In summer, the development of stratification can temporarily limit this exchange, allowing oxygen to be drawn down at depth until the next mixing season. In lower latitude regions where stratification is stronger and persists longer. Mid-depth, oxygen minima may be more stable features bounded above by the well-ventilated mixed layer and below by waters that have been more recently renewed from high-latitude sources. Over geological timescales, the slow shift from the glacial climate toward a more moderate Silurian state influences oxygen patterns in several ways. As sea level rises, the volume of shallow shelf seas increases, expanding the area of sea floor that lies within reach of regular mixing and ventilation. At the same time, changes in wind patterns, storm tracks, and deep water formation sites alter where and how strongly the ocean interior is renewed. The overall trend in many regions is toward a gradual reduction in the most extreme anoxic conditions that characterize some basins during the extinction interval, but this trend is neither uniform nor monotonic. Local episodes of renewed low oxygen conditions can still occur when the balance of production and circulation favors them and different basins follow different trajectories depending on their geometry and connection to the global circulation. The spatial distribution of oxygen thus forms a complex three-dimensional mosaic. Well-mixed oxygen-rich shelf sees neighbour deeper slopes where oxygen minimum zones encroach on the seafloor. Semi-enclosed basins alternate between phases of partial ventilation and intervals of near stagnation. Deep ocean plains hold cold, relatively stable water masses whose oxygen content reflects the conditions in which they were formed, gradually declining as respiration continues until they are eventually replaced by newer waters. Within this mosaic, some regions become suitable for a wide range of bottom-dwelling organisms, while others remain inhospitable and act as barriers or filters for the spread of life. The recovering planet does not move instantly from a low oxygen crisis to a fully ventilated state. Rather, the physical and chemical structure of the ocean passes through intermediate stages in which oxygen is redistributed by wind currents and biological demand, creating the backdrop against which other aspects of post-extinction recovery will unfold. In the early Silurian oceans, the movements of nutrients and carbon link the recovering climate to the conditions that marine life experiences from the surface to the deep basins. The Ordovician glaciation has reworked vast areas of continental crust, grinding rocks beneath ice sheets and leaving behind thick deposits of debris along their margins. As ice retreats and meltwater begins to flow more steadily, these freshly exposed materials interact with the atmosphere and with liquid water. Chemical weathering of silicate and carbonate rocks proceeds wherever temperature and moisture allow, releasing dissolved ions into rivers and groundwater. Calcium, magnesium bicarbonate and other weathering products travel slowly toward the sea, where they enter the ocean as part of a continuous flux that helps to regulate both nutrient supply and the carbon cycle. In cold regions still influenced by seasonal snow and ice, weathering remains relatively slow compared with warmer, wetter climates, yet the sheer extent of the newly exposed surfaces means that significant amounts of material are still mobilized. Fine rock flour produced by glacial grinding can be carried in suspension by meltwater streams and rivers, giving them a high load of mineral particles and associated trace elements. When these waters reach the coast, part of this load settles near river mouths, building deltas and coastal plains, while a finer fraction remains in suspension and is carried out onto the flooded shelves. There the smallest particles eventually sink through the water column or are transported along the seabed by bottom currents, contributing to a blanket of silt and clay that covers large areas of the continental margins. The dissolved component of weathering, including important nutrients such as phosphorus, also enters the sea. Phosphorus often attaches to mineral surfaces in soils and sediments on land, but erosion and runoff can transfer it into the dissolved phase. Once in seawater, phosphorus can be taken up by phytoplankton and other primary producers, supporting the rebuilding of marine food webs. Nitrogen, another key nutrient, cycles through the atmosphere and ocean, primarily via biological processes such as nitrogen fixation and denitrification, but its availability is influenced by the productivity and redox conditions of the ocean that have been reshaped by the extinction interval. As circulation patterns adjust and low oxygen zones expand or contract, the balance between nitrogen sources and sink shifts, setting background constraints on how much primary production the surface ocean can sustain. In many recovering shelf seas, the nutrient inputs from land combine with physical processes in the ocean to structure where and when primary producers can flourish. Along some coastlines, winds drive surface waters away from the shore, and cooler subsurface waters rise to replace them. These upwelled waters carry nutrients that have accumulated at depth through the remineralization of sinking organic matter. When they reach the sunlit surface, they mix with river-borne nutrients and support blooms of phytoplankton. In other regions, weak upwelling or strong stratification limits the upward transport of deep nutrients, and primary production must rely more heavily on the nutrients supplied directly from the atmosphere and rivers, or recycled within the mixed layer. The vertical structure of the ocean, with its mixed layer thermocline and deep waters, thus interacts with the river-driven delivery of dissolved materials to shape the nutrient landscape of the recovering seas. Over longer timescales, the global carbon cycle mediates the link between weathering ocean chemistry and climate. When silicate minerals on land are weathered, they consume carbon dioxide from the atmosphere and produce bicarbonate ions that are carried to the ocean. Once in seawater, these ions can combine with calcium to form carbonate minerals that are eventually buried in sediments. This sequence transfers carbon from the atmosphere to the solid Earth and acts as a long-term thermostat tending to cool the climate when weathering rates are high. During the peak of Ordovician glaciation, low temperatures and the presence of ice over large areas reduce some forms of weathering, but the exposure of large continental shelves and glacially produced debris created new surfaces for reaction. As the climate relaxes toward a milder Silurian state, and precipitation patterns change, the balance between these processes shifts. Some regions experience increased runoff and chemical weathering, drawing down atmospheric carbon dioxide, while others remain cold and arid, limiting further change. The ocean responds to changes in atmospheric carbon dioxide through gas exchange at the surface. When atmospheric carbon dioxide is higher than the partial pressure in surface waters, carbon dioxide dissolves into the ocean, where it reacts with water to form bicarbonate and carbonate ions. When the opposite is true, carbon dioxide can be released back to the atmosphere. The recovering early Silurian ocean is not in perfect equilibrium at every location, but over large areas the system tends toward a balance set by global carbon inputs, from volcanism and metamorphism on one side, and carbon removal by weathering and burial on the other. Within the ocean, the biological pump, which is the sum of processes by which organisms transfer carbon from the surface to depth, continues to operate. Phytoplankton in the sunlit upper waters incorporate dissolved inorganic carbon into organic matter through photosynthesis. Some of this carbon is passed along to grazers and predators in the surface layer, where it is respired back to carbon dioxide, while a fraction sinks as particles into deeper waters. As these particles descend, bacteria and other decomposers break them down, consuming oxygen and releasing carbon dioxide and nutrients. This process enriches deep waters in dissolved inorganic carbon and nutrients relative to the surface. When deep or intermediate waters eventually return to the surface through upwelling or mixing, they bring this stored carbon and nutrient inventory back into contact with the atmosphere and the photic zone. In the wake of the extinction, the efficiency and spatial pattern of this biological pump may be altered, because the composition of plankton communities and the structure of food webs are changing. Even so, the basic coupling between surface productivity, sinking organic matter, and deep water chemistry remains a central feature of the ocean carbon cycle. The burial of organic carbon in sediments provides another path for long-term carbon storage. When some fraction of the organic material produced in surface waters escapes complete decomposition and is buried in seafloor sediments, it removes carbon from the short-term cycle and can influence atmospheric composition over millions of years. During intervals of widespread low oxygen or anoxia at the seafloor, organic carbon is more likely to be preserved because conditions are less favourable for organisms that normally consume it. Evidence from rock records indicates that the end Ordovician extinction and its immediate aftermath are associated with shifts in carbon isotope ratios that suggest episodes of enhanced organic carbon burial. In the early Silurian recovery, as low oxygen conditions become more restricted in time and space, the locations and intensity of organic carbon burial adjust. Some deep basins may continue to act as important sites of preservation, while better ventilated shelves favour more complete recycling of organic matter back into carbon dioxide and nutrients. The overall effect on atmospheric carbon dioxide depends on the balance between these different settings. Regional differences in nutrient supply produce a patchwork of productivity regimes across the globe. Along some high-latitude Gondwanan margins, meltwater and glacial sediments supply minerals and nutrients to cold shelf seas, but strong seasonal mixing and variable light conditions limit the duration of high productivity periods. In equatorial, epicontinental seas over Laurentia and Baltica, warmer temperatures and longer growing seasons allow more sustained primary production, provided that nutrients are replenished by upwelling river input or internal recycling. Semi-enclosed basins behind island arcs may experience episodes of high productivity, followed by oxygen depletion at depth, as nutrient-rich waters support intense surface blooms, whose decay draws down oxygen in deeper layers. These local patterns feed back into the global carbon cycle by affecting where carbon is buried, where it is returned to the atmosphere, and how nutrients are stored or released. Over multi-million-year timescales, these processes leave a record in marine sediments. Alternating layers of carbonate-rich and organic-rich deposits, variations in the types of minerals that carry phosphorus, and shifts in carbon isotope ratios all reflect the history of nutrient delivery, productivity and carbon burial. In the early Silurian, these signals show that the Earth system is moving away from the extreme conditions associated with the glaciation and extinction, but still exhibits substantial variability as it searches for a new long-term balance. The distribution of nutrients and carbon in the recovering oceans is thus not uniform but structured by the interaction of weathering on land, runoff ocean circulation and biological activity. In shallow seas, high exchange with the atmosphere and land inputs make conditions sensitive to regional climate and tectonics, while in the deep basins the slow turnover of water and the legacy of earlier events maintain distinct chemical signatures. Together, these factors define the chemical environment in which marine life must operate during the first steps of recovery from the earliest global mass extinction of complex organisms, linking the fate of living communities to the quiet but persistent reshaping of rocks, waters, and dissolved substances throughout the planet. As the early Silurian seas spread once more across the edges of continents, the architecture of the seafloor begins to define where life can return and how it can persist. The broad continental shelves that had been exposed during the low sea level of peak glaciation now lie beneath tens to a few hundreds of meters of seawater, forming wide, gently sloping platforms that extend from the new shorelines toward the continental slopes. On these shelves, depth increases gradually, and even at their outer edges, sunlight can still reach the seafloor, where waters remain relatively clear. The physical character of these shelves depends on their glacial and tectonic history. In some regions, former glacial outwash plains now lie flooded, mantled by a veneer of sand and gravel that was reworked by waves and currents as the sea advanced. In others, older bedrock surfaces are only thinly covered by sediment and ridges. Knobs and eroded channels on the underlying rock still influence the pattern of currents near the bottom. The continued input of sediment from rivers and the remobilization of older deposits by storms mean that the seafloor is not static. Waves generated by storms propagate across shallow shelves and stir the upper layer of sediment, especially in coastal zones and on shoals. During large storm events, the combined action of waves and currents can move sand and shells along the seabed, forming ripples, dunes, and sheets that migrate slowly over time. Between such events, calmer conditions allow finer silt and clay particles to settle from the water column onto quieter parts of the seafloor, especially in deeper or more sheltered areas of the shelves. This interplay between energetic and quiet periods produces a mosaic of substrate types from coarser sands and gravels in high-energy zones to soft muds in protected depressions. Along parts of the continental margins, the shelves narrow and give way more abruptly to steeper slopes. Here, gravity-driven processes play a larger role in shaping the habitat. Where thick accumulations of sediment on the shelf edge become unstable, they can fail and flow downslope as turbidity currents, which are dense sediment-laden flows that travel along the seafloor. These flows deposit graded beds of sand and mud on the slopes, and in the deeper basins below, forming submarine fans that spread outward from the base of the slope. Between such events, the slopes may be draped by a steady rain of fine material from the overlying water column. The result is a layered architecture in deeper settings, with relatively coarse event-driven deposits interbedded with finer, more continuous sediments. The stability, grain size, and oxygenation state of these layers will later influence which kinds of organisms can occupy them when biological communities reassemble. Superimposed on this broad framework of shelves and slopes are localized hard grounds and topographic highs that provide more rigid substrates. In some places, early Silurian seas host modest carbonate mounds and reef-like structures built by communities of skeletal organisms and microbes that persist despite the extinction. These structures are not as extensive or towering as some later reefs in Earth history, yet they still rise above the surrounding seafloor and create three-dimensional relief. Framework-building organisms secrete carbonate skeletons that interlock or accumulate while microbial mats and encrusting forms bind the surfaces between them. Over time, waves and storms break some of this material into fragments that are trapped in the growing framework or spilled onto nearby soft substrates. The result is a patchwork of solid, rough surfaces, rubble aprons, and adjacent sediment-covered areas. Such heterogeneity in physical structure increases the range of microhabitats available for future colonists. Carbonate platforms may also form in areas where clear, warm, shallow waters favour the direct precipitation of carbonate muds and the accumulation of skeletal debris. On these platforms, the seafloor can be relatively firm where cementation has progressed, or softer where fresh sediment blankets the surface. In tidal zones and very shallow subtidal areas, rhythmic currents can build bars and ridges of carbonate sand that migrate with changing water flow, while deeper parts of the platform collect finer material. The edges of these platforms where they transition into deeper water may be marked by breaks in slope and changes in substrate type, adding further variety to the habitat architecture. Not all shelves are dominated by carbonates. In many regions, siliciclastic sediments derived from the erosion of continental rocks dominate the fill. There, the character of the seafloor reflects the balance between river input wave energy and the settling of fine particles. Estuaries and deltas at river mouths deliver alternating pulses of sand silt and clay, constructing lobes that prograde into the sea. Distributary channels carry coarser material seaward, while overbank and flood events spread finer sediments across adjacent areas. As sea level rises and shorelines retreat, some deltic deposits become stranded beneath new marine waters, their distributary patterns preserved as subtle relief on the shelf surface that can steer subsequent currents. In quieter embayments and the interiors of epicontinental seas, muds accumulate more continuously, forming broad expanses of relatively uniform soft substrate. Beyond the shelves, the deep ocean basins present a different architectural context. Their floors lie well below the reach of storm waves, and sedimentation is controlled mainly by the slow settling of fine particles and the occasional arrival of material carried downslope from the margins. The deep sea floor is comparatively smooth at large scales, though it is interrupted by features such as abyssal hills, seamounts, and fracture zones inherited from seafloor, spreading and tectonic processes. Sediments in these settings tend to be fine-grained, accumulating as thin, laterally extensive layers that blanket the underlying basaltic crust. The thickness of this sediment cover varies with distance from the continents and with the history of input from margins and the overlying water column. In basins that experience severe low oxygen conditions during the extinction interval, the uppermost layers may include dark organic rich muds, laid down under poorly ventilated waters, capped in the early Silurian by lighter coloured sediments as conditions change. At a smaller scale, the arrangement of grains and particles at the sediment surface defines microhabitats that will later matter for meiofauna and microbial communities. Coarser sands allow water to flow more readily through the pore spaces between grains, bringing oxygen and dissolved substances into contact with buried layers. Fine muds impede such exchange, making the sediment more prone to developing sharp redox gradients just below the surface. Where bottom currents are strong enough to winnow away fine particles, lag deposits of coarser material or shell hash can form, creating pavements of skeletal debris or pebbles. In contrast, in very low energy environments, a flocculent layer of suspended and recently settled particles can cover the seabed, making the boundary between water and solid substrate more gradual. Across the seafloor, this spatial arrangement of different substrate types is not random. Bathymetry, which is the variation in depth and shape of the seafloor channels, currents and controls where sediments are eroded, transported or deposited. Troughs and depressions tend to collect fine material, while highs and ridges are more often sites of erosion or non-deposition. Along some shelf edges, internal tides and contour following currents shape drifts and moats of sediment, carving one slope segment while building deposits on another. Over time, these processes sculpt a complex three-dimensional landscape that is dynamic on geological timescales, yet appears stable over shorter intervals. Water depth, substrate firmness, and the degree of exposure to waves and currents together define the basic niches that the seafloor can offer. In very shallow zones near shore, frequent disturbance by waves and shifting sands will later select for organisms that can tolerate or exploit constant change. Slightly deeper in areas where storms are less able to mobilize the bed, more stable sands or muds permit different strategies. Around hard grounds, mounds and reef-like structures, the presence of vertical relief and firm attachment sites allows a contrasting set of life forms to gain a foothold. In deeper water, where light no longer reaches the seabed and physical disturbance is rare, the architecture is simpler, but gradients in oxygenation and sedimentation still create distinctions between more and less favourable areas. The early Silurian seafloor thus offers a spectrum of physical conditions from shifting coastal sand bodies and expanding mud plains on flooded shelves to scattered carbonate mounds and extensive deep sea plains. This physical template laid down by the interplay of sea level rise sediments, supply tectonics and ocean energy sets the stage on which the biological components of recovery will later reorganize, determining where refugees can persist, where recolonization can proceed quickly, and where the scars of the extinction will linger longest in the structure of marine habitats. On the early Silurian seafloor, hard substrates and three-dimensional structures begin to stand out against the broad expanses of sand and mud that cover most continental shelves. These solid features are not continuous walls or barrier systems, but scattered mounds, low ridges and patch reefs that rise modestly above the surrounding seabed. Many are built from the skeletons of organisms that survive the end Ordovician crisis or diversify soon after, while others are produced by the interaction of microbial growth, sediment binding and early cementation. Together they form a set of localized elevations and firm surfaces that modify near bottom water flow alter patterns of sediment deposition and create a more varied physical landscape. In regions where water is clear, relatively warm, and within the reach of regular wave and current energy, skeletal carbonates accumulate. Tabulate and rugose corals, stromatoporoids, which are sponge-like organisms that secrete massive calcareous skeletons and various other shell-forming groups contribute pieces of rigid framework. Individual colonies or skeletons grow on existing hard patches of seafloor, along ridges of lithified sediment, or on earlier carbonate accumulations. As these skeletons stack and intergrow over many generations, they build irregular mounds and knolls that can reach several meters above the surrounding substrate. Between and within the skeletal elements, lime mud and skeletal debris fill gaps stabilized by early cementation and by the presence of microbial films that bind grains together. The resulting structures are not yet the extensive high-relief barrier reefs of some later periods, but they do possess enough relief to influence local circulation. Water flowing across a shelf encounters these mounds and is deflected upward and around them. This deflection creates zones of slightly accelerated flow over mound crests and areas of reduced flow in their lees. Faster currents over the top can winnow away fine sediment, keeping surfaces relatively clean and firm, while slower currents on the flanks and down current sides allow fine particles to settle and accumulate. In this way, each mound develops its own pattern of sediment distribution: coarser, better washed materials near the top, and finer, softer sediments in adjacent depressions and sheltered pockets. Where skeletal builders are less abundant or conditions do not favour their growth, microbial communities still play an important role in generating hard substrates. On gently sloping shelves and on localized highs, microbial mats trap and bind sediment grains, gradually building layered structures known as microbialites. Over time, repeated trapping and binding, combined with the precipitation of carbonate minerals within and around the mats, produces lithified domes, columns, and crusts that stand slightly above the surrounding seafloor. These microbial mounds and pavements can occur in shallow subtidal zones, where light remains available to support photosynthetic microbes, and where water energy is sufficient to supply new sediment grains, but not so strong as to strip away the developing mats. The surfaces of these lithified microbialites are firm and often irregular, with small ridges, pits, and steps created by growth patterns and localized erosion. Not all hard grounds in the early Silurian are biogenic frameworks. In some areas, early cementation of carbonate muds on the seafloor creates laterally extensive hard grounds that are then exposed by erosion or non-deposition. These cemented layers can form when the chemistry of pore waters in the upper sediment column favours the precipitation of calcite or other carbonate minerals that glue grains together. When sea level sediment supply or currents change, subsequent erosion may remove the softer sediments above these layers, leaving a relatively smooth but firm surface at the sediment-water interface. Such hard grounds can extend over many square kilometres, forming flat to gently undulating pavements, interrupted only by small relief features. They provide widespread firm substrate in settings that would otherwise be dominated by softer muds and sands. Around the margins of islands, carbonate platforms and uplifted blocks of older rock wave and current action can also generate rocky shores and subtidal rock surfaces. Here the substrate consists of coherent bedrock, or large blocks and boulders of lithified material derived from cliffs and slopes. In very shallow water, wave energy may be intense enough to prevent the accumulation of fine sediment, leaving surfaces swept clean and exposing fractures, joints, and bedding planes. As depth increases beyond the zone of most vigorous wave action, these rock surfaces may be covered by a thin drape of sediment but still remain relatively firm. The irregular relief of such areas with ledges overhangs and pockets adds another category of hard substrate distinct from the more rounded carbonate mounds of the open shelf. The presence of these various hard substrates alters the physical structure of the water column immediately above the seafloor. Low mounds and ridges create small-scale pressure differences as currents flow over and around them, generating turbulent eddies that enhance mixing in the lower part of the water column. This mixing can affect how suspended particles are delivered to different parts of the seafloor, concentrating them in some locations while keeping others comparatively sediment-free. In turn, the spatial pattern of sedimentation and erosion helps to maintain the relief of hard features by preferentially depositing material in low areas and removing it from highs. In some shelf settings, repeated storm events interact with this relief. Storm waves and surge can temporarily increase bottom shear stresses across broad areas, mobilizing sediment and scouring around the bases of mounds, while only lightly affecting their higher surfaces. After the storm, resettling particles are more likely to accumulate in scoured depressions and along the flanks rather than on the crests. Over many such cycles, mounds can become surrounded by moats or depressions that accentuate their apparent height relative to the surrounding seabed. The depth range over which these hard structures occur depends on both sea level and water clarity. In the shallowest zones, wave action may be too intense for delicate skeletal frameworks to persist, favouring instead low relief, robust forms and rock surfaces, slightly deeper where waves still stir the seafloor, but with less destructive force. Skeletal mounds and microbialites can establish themselves, benefiting from both light for photosynthetic partners and sufficient water movement to deliver dissolved substances and remove waste. At greater depths beyond the reach of strong wave action, and below the limit of photosynthetically useful light, only those hard substrates derived from earlier phases of growth or from erosion of lithified layers remain. These deeper hard grounds and outcrops occur sporadically on slopes at the edges of platforms and in parts of the deep basin floor where tectonics or past depositional patterns have left rock exposed. Across the broad scale of the early Silurian oceans, hard substrates are much less common in area than soft sediments, but their influence is amplified by the way they concentrate relief and modify flow. From small carbonate mounds and microbial domes on open shelves to extensive cemented pavements and rocky margins around islands and platforms, each hard feature adds detail to the seafloor architecture. They create gradients in elevation firmness and exposure to currents over scales of meters to tens of meters, nested within the larger patterns of shelf width, slope angle and basin depth. In combination with the distribution of sands, silts and muds, this patchwork of hard and soft surfaces defines the physical template at the habitat scale on which post-extinction marine life will operate, setting limits on where attachment shelter and stable occupancy are physically possible, even before any particular community takes advantage of these opportunities. As the physical structure of the early Silurian oceans settles into a new pattern, light again becomes the starting point for most energy flow through marine systems. Sunlight enters the upper ocean, where it is absorbed, scattered and reflected by water molecules, dissolved substances and suspended particles. The depth to which useful light penetrates varies from place to place. In clear offshore waters above deep basins, the zone of effective photosynthesis extends tens of meters below the surface, while in turbid shelf seas laden with fine sediment and plankton, it is compressed into a shallower band. Within this photic zone, microscopic primary producers rebuild the base of the food web. Phytoplankton, which are microscopic algae and cyanobacteria that live freely in the water, column float or weakly swim in the sunlit layer. Many of the main groups that had dominated Ordovician seas persist across the extinction boundary, although their diversity and abundance have been altered. Organic walled microfossils known as acritarchs, which represent a variety of planktonic algae, continue into the Silurian with a reduced but still significant presence. Their morphologies change over time as new forms appear and others vanish, reflecting both evolutionary innovation and the filtering effect of the extinction. Siliceous and calcareous algae contribute as well, though their skeletal remains are less conspicuous in many sediments of this age. Cyanobacteria capable of oxygenic photosynthesis remain important in both planktonic and benthic settings. In the surface ocean, the distribution of these planktonic producers is controlled by the interplay between light nutrients and physical mixing. In regions where the mixed layer is shallow and nutrients are available, phytoplankton populations can grow rapidly, converting dissolved inorganic carbon and nutrients into organic matter. When the mixed layer deepens during storms or seasonal cooling, phytoplankton are mixed into darker waters, where light is insufficient to support continued growth, and their net production declines until stratification returns or they adjust to new conditions. In high latitude, shelf seas, strong seasonality produces marked cycles, long low light winters with little production, followed by springs and summers in which increasing light and nutrient-rich surface waters allow pronounced blooms. In equatorial and mid-latitude regions where changes in day length and surface temperature are less extreme, production can be more continuous but still responds to episodic events such as upwelling pulses or river-borne nutrient inputs. Vertical stability plays a crucial role. In areas with strong stratification, such as warm epicontinental seas or open ocean gyres, nutrients in the surface layer can be depleted by sustained phytoplankton growth. Once this depletion occurs, further production depends on the recycling of nutrients within the mixed layer and on the slow leak of nutrients upward from deeper waters through diffusion and intermittent mixing. In contrast, where winds, tides and currents regularly mix the upper water column or bring deep water to the surface, nutrients are replenished more rapidly, supporting higher sustained productivity as long as light remains sufficient. Upwelling zones along some continental margins and island arcs represent such environments where the rising of deeper nutrient-rich water fuels surface phytoplankton communities even under relatively strong stratification above. In addition to free-floating plankton, primary producers inhabit the seafloor wherever light reaches the bottom and conditions permit. In very shallow subtidal zones and intertidal flats of epicontinental seas and nearshore shelves, microbial mats composed of cyanobacteria and other simple phototrophs carpet patches of sediment and hard substrate. These mats bind grains together and may form thin cohesive layers that trap fine particles and precipitate carbonate minerals. Over time, repeated growth, burial and lithification can produce microbialates, but even before any lithification occurs, the living mats themselves capture sunlight and convert it into organic matter that feeds local microfaunal and meiofaunal communities. Algal filaments and small multicellular algae may also colonize shallow substrates, especially in clear water settings where wave and current energy do not exceed their capacity to remain attached. On the flanks and tops of carbonate mounds and reef, like structures, symbiotic and independent photosynthetic organisms contribute to both energy capture and skeletal growth. Some corals and stromatoporoids likely host photosynthetic partners that supply part of their metabolic needs, while surface microbial films and algae coat exposed skeletal surfaces, adding a thin additional layer of primary production. In such settings, light not only supports the growth of the framework builders themselves, but also contributes to the local productivity that sustains associated communities of grazers and filter feeders. Even below the depth where light supports robust macroalgal growth, low levels of illumination can still allow some photosynthesis by specialized microbes extending the vertical range over which primary production occurs, albeit at reduced rates. Recovery of primary production after the end-Ordovician extinction does not proceed uniformly across all basins. Evidence from the rock record, including the abundance and diversity of phytoplankton microfossils and the nature of organic matter preserved in sediments, indicates that some regions experience relatively rapid rebounds in productivity, while others remain subdued for longer intervals. This patchiness reflects local combinations of nutrient supply mixing regimes and the severity of prior low oxygen conditions. In basins where deep waters remain oxygen poor, or where stratification remains strong, the recycling of nutrients from depth back to the surface can be limited, slowing the re-establishment of high surface productivity. On well-ventilated shelves, by contrast, seasonal overturning and river inputs bring nutrients to the photic zone more efficiently, fostering quicker recovery of primary producer populations. The composition of recovered primary producer communities also differs across environments. In some epicontinental seas, organic walled microplankton show a diversification of forms during the Silurian, suggesting that new algal lineages or ecological strategies are taking hold. These changes may influence how efficiently different size classes of plankton can capture light-resist grazing or sink, as particles thereby affecting the structure and export of organic matter. Simple filamentous algae and cyanobacteria likely dominate benthic phototrophic communities in many shallow areas, with the balance between mat-forming microbes and more upright forms depending on substrate type, water depth, and wave energy. In offshore waters, small phytoplankton that can remain suspended in the upper ocean may fare better than larger forms that sink more rapidly, especially in regions where stratification is strong and mixing weak. The link between primary production and oxygen patterns persists. In well-ventilated regions where the supply and loss of oxygen remain balanced, increases in primary production enhance the capacity of surface waters to generate oxygen through photosynthesis without driving severe oxygen depletion at depth. In contrast, in semi-enclosed basins with restricted deep water renewal, high primary production can contribute to the development or persistence of low oxygen zones, as sinking organic matter is decomposed in deeper layers. Thus, areas of strong primary production and areas of low oxygen can coincide, especially where physical renewal is limited, even though one represents an energetic upper ocean and the other a stressed subsurface environment. The recovering primary producer base also starts to influence the cycling of other elements. As phytoplankton grow, they take up not only carbon and major nutrients, but also trace metals that act as cofactors in metabolic processes. When they die and sink, these elements are carried to the sediments where they may be buried or returned to the water through diagenetic reactions. Over time, this cycling contributes to regional differences in the geochemistry of sediments and the water column. In sediments deposited under well-oxygenated conditions, the organic matter from primary producers is more thoroughly degraded, and associated trace elements are released back into pore waters and bottom waters. In low oxygen settings, organic matter preservation is higher, and some trace elements may become concentrated in the sediment, providing clues in the rock record to the intensity and distribution of former productivity and redox states. Primary production on the seafloor extends beyond open marine settings. In restricted lagoons, tidal flats, and sheltered embayments that now fringe flooded coasts, microbial and algal mats form dense carpets during favourable seasons, only to be periodically disrupted by storms, desiccation, or burial by new sediment. These dynamic shallow environments contribute pulses of organic matter and fine sediment to adjacent subtidal zones, linking coastal and shelf productivity. As simple plants slowly begin to expand on land, in some regions their presence near shorelines may also influence nutrient delivery and sediment stability, although during the early Silurian their contribution remains limited compared with that of marine and microbial primary producers. Across the recovering world, ocean therefore a layered network of light-driven activity spreads from the surface down to the depth, where usable light flickers out, and across the seafloor, wherever photons still reach. Microscopic phytoplankton in the open sea, filamentous algae, and microbial mats in shallow waters, and photosynthetic partners in skeletal builders all participate in capturing solar energy and converting it into chemical form. This distributed system of primary production re-establishes the flow of energy that will support the rebuilding of herbivore and detritivore populations, the return of complex food webs, and the gradual diversification of marine life in the wake of the first major extinction of complex organisms, even though at this stage the focus remains on the quiet, continuous work of producers themselves and the physical and chemical settings that allow them to function. In the early Silurian seas, as primary producers regain their foothold in the surface waters, and on illuminated sea floors, the flow of energy through marine food webs begins to rebuild layer by layer. The organic matter produced by phytoplankton, benthic algae, and microbial mats does not remain unused. It is grazed, filtered, and decomposed by a range of organisms that either survive the Ordovician crisis or originate during the early stages of recovery. These consumers in turn support predators and scavengers, which link different parts of the ecosystem and gradually re-establish the complex pathways along which energy and matter move from one group to another. In the plankton of the open ocean and epicontinental seas, small herbivorous and omnivorous zooplankton form the first major bridge between primary producers and higher levels in the food web. Tiny crustaceans and other microplankton feed on phytoplankton cells and small particles of organic matter suspended in the water. They filter, grasp, or trap their food as they drift or swim through the mixed layer. Each individual consumes only a minute amount, but taken together. These planktonic grazers process a large share of the organic matter produced in the photic zone. Their feeding converts dispersed microscopic cells into more concentrated forms of biomass, including their own bodies, and the fecal pellets they produce. Fecal pellets, being denser than individual cells, sink more rapidly, transferring organic material downward into deeper water. Some of this material is intercepted by other consumers in the upper ocean. Some continues its descent where it becomes food for deeper-dwelling organisms and microbes. Larger zooplankton and nectonic animals feed on the smaller grazers. Among them are early representatives of pelagic arthropods and small jawless vertebrates that inhabit the mid-water column and the upper parts of the deep basins. Jawless fishes or agnathons with simple mouths, adapted for sucking or filter feeding, move through the water column, taking in plankton and small particles. Their activity forms an intermediate trophic level, connecting the microscopic world of phytoplankton and small zooplankton to the more conspicuous vertebrate predators that will expand later in the Silurian. Other mid-level consumers include pelagic larvae of benthic invertebrates, which feed in the plankton before eventually settling to the seafloor, thereby linking pelagic and benthic compartments of the ecosystem. In coastal and shelf settings, primary production also supports rich benthic communities. On soft sediments of shallow shelves deposit feeders, and suspension feeders play central roles in rebuilding energy flow. Burrowing worms and other infaunal organisms ingest sediment, extracting organic particles and microbes from the grains. Surface deposit feeders graze across the sediment-water interface, consuming films of bacteria, microalgae, and fine detritus. Suspension feeders, including brachiopods, bivalve mollusks, and some arthropods, filter particles from the water column, capturing phytoplankton, small zooplankton, and suspended detritus. These organisms anchor themselves in or on the sediment, or attach to firm substrates where available, and pump water across feeding structures that capture food. Their feeding not only transfers energy from the water column to the seafloor, but also clarifies the water, locally influencing light penetration and the distribution of particles. On and around hard substrates such as carbonate mounds, microbialites, and rocky outcrops, a different but related suite of consumers develops. Encrusting filter feeders colonize exposed surfaces, forming pavements of organisms that extend into the passing current. Their feeding is enhanced by the locally accelerated flows generated around mounds and ledges. grazers move across these surfaces, scraping microbial films and algae. Mobile predators hunt among the crevices created by skeletal frameworks and attached organisms. The presence of relief concentrates these interactions in 3 dimensions, producing complex small-scale networks of feeding relationships that sit atop the broader patterns of shelf and basin circulation. Scavengers and detritivores provide a crucial link between living communities and the pool of dead organic matter. When organisms die, their bodies rarely remain intact on the seafloor for long. Benthic scavengers, including some trilobites, early eurypterids and other arthropods, search for carcasses and large fragments, breaking them into smaller pieces and consuming soft tissues. Their activity accelerates the fragmentation of organic matter, making it more available to smaller deposit feeders and microbes. In deeper waters, where carcasses and large particles reach the seafloor after sinking through the water, similar processes occur at a slower pace, mediated by organisms adapted to low light and low food flux conditions. The deeper seafloor, especially in regions where oxygen remains sufficient to support animal life, hosts a set of detritus-based food webs that rely primarily on the rain of organic material from the surface. Microbial communities permeate all levels of these food webs. Bacteria and archaea colonize particles of organic matter as they sink through the water column, as they accumulate on or in the sediments, and as they line the burrows of infaunal organisms. These microbes break down complex organic molecules into simpler compounds, releasing nutrients and carbon dioxide. They can also form symbiotic relationships with animals, providing a source of nutrition in exchange for shelter or access to substrates. The microbial loop in which bacteria and other microbes assimilate dissolved organic compounds and are then consumed by small protozoans and metazoans recycles energy and materials at small scales, but has large-scale consequences for how efficiently organic matter moves to higher trophic levels or to the deep ocean. Not all energy transfer paths are direct or efficient. At each step, from primary producers to higher consumers, some fraction of the organic matter is respired, converted to heat, or lost as refractory material that resists further breakdown. Some production in the surface ocean bypasses complex food webs entirely as organic matter is buried in sediments under conditions that limit decomposition. Nevertheless, as consumer communities rebuild, the proportion of primary production that enters structured food chains increases in many regions compared with the stressed conditions during the extinction. Herbivory predation and scavenging combine to produce more continuous and interconnected pathways of energy flow. Predators occupy key positions in these recovering networks. On the seafloor, eurypterids, straight-shelled nautiloid cephalopods and larger arthropods prey on smaller invertebrates and each other. Their hunting behavior concentrates energy from a broad base of prey into relatively fewer individuals at higher trophic levels. In the water column, predatory nekton feed on zooplankton and smaller fishes, while some graptor-like colonies drifting in the plankton may function as passive suspension feeders capturing tiny particles. Although many apex predators of the early Silurian are still modest in size compared with later Paleozoic forms, they nonetheless exert top-down influences on their ecosystems, affecting the abundance and behavior of their prey. The spatial structure of food webs reflects the underlying physical environment. In nutrient-rich upwelling zones and well-mixed shelf seas, high primary production supports dense populations of zooplankton and benthic consumers, which in turn sustain larger predators and scavengers. Food webs here tend to be relatively short and broad, with many parallel pathways and redundancy among consumer types. In contrast, in oligotrophic open-ocean gyres, where nutrient supply is limited and stratification is strong, primary productivity is lower, and food webs may be more elongated, passing through several steps of small consumers before reaching larger predators. In semi-enclosed basins with fluctuating oxygen levels, food webs are constrained both by the depth of habitable waters and by the periodic expansion of low oxygen zones. Benthic communities may be restricted to shallow areas, while deeper regions remain dominated by microbial processes that do not require oxygen. Temporal variability further shapes these networks. Seasonal blooms of phytoplankton in high-latitude seas support pulses of zooplankton growth and reproductive activity in higher consumers, followed by periods of relative scarcity. These pulses send waves of organic matter downward each year, sustaining benthic detritus-based food webs and influencing the timing of reproduction and growth in bottom-dwelling organisms. In lower latitudes, where seasonality is less pronounced, more continuous but less intense, primary production supports a different dynamic with steadier but lower amplitude flows of energy through the system. Over millions of years, the structure of these food webs will leave an imprint in the rock record through patterns of fossil occurrence trace fossils that record feeding and burrowing activity and geochemical signals tied to organic matter processing. In the immediate recovery interval, however, the emphasis lies on the stepwise reconnection of producers, consumers, and decomposers in different parts of the ocean. As survivors of the extinction expand their ranges and new lineages appear, the variety of feeding strategies increases. Filter feeders exploit currents over hard grounds and mounds. Grazers track the spread of microbial mats and algal films. Deposit feeders process the expanding blankets of sediment on flooded shelves. Predators and scavengers move among these groups, linking them into a network that transfers energy from light captured in the surface ocean to the deepest ventilated parts of the seafloor. The early Silurian food webs are not yet as complex or stable as those of later periods, and they differ from the pre-extinction Ordovician systems in their taxonomic composition and spatial arrangement. Yet they accomplish the same fundamental task, the redistribution of energy and matter, through a chain of physical and biological processes that sustains life in the oceans under a new set of climatic and chemical conditions. As physical conditions in the oceans become less extreme and the architecture of habitats stabilizes, the surviving organisms begin to fill the available spaces in new ways. The end Ordovician extinction has removed many species and entire lineages, especially among groups that had flourished on shallow shelves and in the plankton. In the early Silurian, the communities that grow back are shaped both by the legacy of those losses and by the opportunities opened on the reorganized seafloor. In shallow marine settings, brachiopods remain among the most conspicuous shelly animals. Many Ordovician families have been reduced in diversity or eliminated, but others persist and begin to radiate into habitats that are once again suitable. On soft sediments of flooded shelves, brachiopods with simple biconvex shells anchor themselves by pedicles or rest freely on the sediment surface, forming low-density carpets in some areas and more concentrated patches in others. Their distribution reflects subtle differences in water depth, substrate type, and local oxygen levels. Some clades that had been marginal before the crisis now become more common, replacing once dominant forms in particular depth bands or regions. Bivalve mollusks, which already occupied a range of infaunal and epifaunal roles before the extinction, continue to expand. Small burrowing bivalves sift through the upper layers of muddy and sandy sediments, while others live partially buried with siphons extended into the water column. In some settings, bivalves increase in relative abundance compared with brachiopods, especially where sediment is unstable or where frequent disturbance favours mobile and infaunal life habits. Their shells contribute to the accumulating shell hash on the seafloor, adding a new textural component to some habitats. Trilobites, once diverse and abundant on many Ordovician shelves, show a more subdued presence. Many lineages disappear during the extinction, and those that persist are often less numerous and more restricted in their environmental ranges. Early Silurian assemblages in several basins are dominated by a smaller set of trilobite groups adapted to particular conditions such as deeper shelf muds or specific grain sizes. These survivors continue to occupy roles as sediment grazers, scavengers, and hunters of small benthic prey, but the variety of forms and ecological strategies is reduced compared with pre-extinction faunas. New combinations of brachiopods, bivalves, trilobites, and other benthic taxa thus arise, not because each group is wholly new, but because their relative abundances, spatial distributions, and interactions have shifted. Echinoderms contribute another important component to early Silurian communities. Crinoids, which are stalked echinoderms that anchor to the substrate and filter particles from the water, form meadows in some clear water shelf environments and on the flanks of carbonate mounds. Their crowns extend into currents above the seafloor, capturing suspended food. Other echinoderms, such as cystoids and starfish, occur alongside them, occupying different feeding niches. The diversity and abundance of echinoderms vary among basins, but overall they regain a strong presence in benthic communities, especially in settings with firm substrates and good water movement. On hard substrates, coral and stromatoporoid assemblages begin to rebuild three-dimensional frameworks. Tabulate and rugose corals establish colonies on firm surfaces, often together with stromatoporoids and various encrusting organisms. In many regions, these assemblages are initially patchy and low in relief, forming isolated mounds rather than continuous reef tracts. Over time, within favourable settings of water depth energy and chemistry, these frameworks become more extensive and diverse. Compared with the late Ordovician, the taxonomic composition of the coral and stromatoporoid assemblages is altered, reflecting both extinction losses and early Silurian radiations. The resulting mound communities include a mixture of old lineages that survive new species within those lineages, and some groups that were rare or geographically limited before the crisis, but now find more space to expand. In the plankton, graptolite communities show a pronounced turnover. Many Ordovician forms vanish at or near the extinction interval, and the Silurian is characterized by graptolite faunas that differ in shape and colony structure from their predecessors. New clades of planktic graptolites with revised branching patterns and theca arrangements proliferate in the open ocean and in epicontinental seas. They continue to serve as important suspension feeders in the mid-water column and in the rock record as key index fossils that mark time intervals. Their evolutionary change across the boundary illustrates how planktonic communities can reconfigure quickly in response to environmental stress and recovery, even when their basic mode of life remains similar. Other planktonic groups, such as acritarchs, reflect a similar pattern of extinction and replacement. Early Silurian assemblages often display reduced diversity compared with late Ordovician ones, followed by the appearance of new morphologies as time progresses. These changes may signal shifts in the composition of phytoplankton communities and in the ecological roles of different size classes and functional types. Together with the graptolite record, they indicate that community reassembly in the plankton is dynamic, with survivors and new forms occupying open ecological space under changing nutrient and circulation regimes. Nectonic vertebrates and large arthropods contribute conspicuous elements to reassembling communities in some regions. Jawless fishes diversify in early Silurian seas, with various groups occupying nearshore shelf and offshore habitats. Their external armour and body shapes show a range of adaptations to benthic and pelagic modes of life. Some graze or filter feed near the bottom, while others swim higher in the water column. Their expansion adds new pathways for energy transfer between plankton benthos and higher predators. Eurypterids, often called sea scorpions, occur in nearshore and lagoonal environments, as well as in some open marine settings where they act as active predators and scavengers. Their prevalence varies among basins, but where present they can form a significant part of the macrofauna. In many regions, the pace and style of community reassembly differ between environmental settings. Shallow, well-oxygenated shelves that are steadily flooded by rising sea level often show relatively rapid establishment of benthic communities dominated by opportunistic and generalist species. These taxa tolerate a wide range of conditions and can colonize newly available substrates quickly. Over time, as environments stabilize and competitive interactions intensify, more specialized species join these communities or replace some of the earlier colonists, increasing ecological complexity. In contrast, deeper shelf and basinal environments that remain prone to low oxygen conditions recover more slowly. Their benthic animal communities may be sparse or intermittently absent, confined to intervals when oxygen levels are sufficient to support them. The seafloor in such settings continues to be dominated by microbial processes and low diversity assemblages adapted to fluctuating redox conditions. This contrast between fast recovering shallow zones and more sluggish deeper areas creates a vertical and lateral gradient in the extent and maturity of community reassembly even within the same basin. Geographic differences add another layer to this mosaic. High-latitude Gondwanan shelves influenced by cooler temperatures and seasonal ice host communities that differ in composition from those on tropical Laurentian and Baltican shelves. Some taxa have wide geographic ranges and appear in multiple regions while others remain more restricted, either because of environmental preferences or because physical barriers limit their spread during the early stages of recovery. Epicontinental seas enclosed by land and island arcs may develop distinctive assemblages as well, reflecting local salinity, nutrient conditions and connection to the open ocean. Islands of more advanced recovery thus exist within a broader seascape, where other areas still show the imprint of the extinction. The presence of taxa that disappear from the fossil record during the extinction interval and then reappear later in the Silurian indicates that some lineages persist in refuges that are poorly sampled or rarely preserved only to expand when conditions improve. These returning groups join with continuous survivor lineages and newly originating forms to assemble communities that mix different evolutionary histories. In some cases, pre-extinction ecological roles are refilled by closely related species. In others, the roles are taken up by different groups, altering interaction networks, even where the overall structure of the habitat seems similar. Throughout this interval, community reassembly remains strongly constrained by the physical and chemical backdrop. Oxygen availability sets an upper limit on the depth to which diverse benthic communities can extend. Substrate type and stability determine which modes of life are practical in a given area. Nutrient regimes and primary production patterns influence the amount of energy available to support higher trophic levels. Within these bounds, survivors of the extinction and their descendants arrange themselves into new combinations that reflect both the contingencies of survival and the general rules governing how organisms partition space resources and energy. The early Silurian oceans thus host communities that are recognizably marine and structurally coherent but distinct in detail from those of the pre-extinction Ordovician world, marking a new phase in the history of complex life rather than a simple return to previous conditions. Across the early Silurian world, recovery from the end Ordovician extinction does not proceed as a single uniform process, but instead forms a patchwork of regional outcomes shaped by climate geography and basin history. On high-latitude shelves along the margins of Gondwana, the legacy of glaciation remains strong. Seasonal sea ice still forms in many coastal waters, and cold surface temperatures shorten the productive season in the upper ocean. During long low-light winters, primary production in these regions is minimal, and planktonic communities retreat to a state dominated by hardy forms that can endure extended periods of low resources. When spring and summer return increased sunlight, and the release of nutrients from melting ice and mixing of the water column allow brief but intense bursts of phytoplankton growth. These blooms support pulses of zooplankton and the reproduction of benthic filter feeders and deposit feeders on the shallow sea floor. Yet the short growing season and periodic disturbance by ice movement and storms limit the overall biomass that can accumulate. Benthic communities remain relatively simple and dominated by opportunistic species that can quickly take advantage of favourable conditions and then withstand extended intervals of stress. In somewhat deeper high-latitude settings, where seasonal mixing does not always reach the seafloor, and where cold, dense waters intermittently sink along the shelves, the oxygenation state of bottom waters varies. Some troughs and depressions may experience recurrent low oxygen, restricting the presence of larger animals and favouring microbial processes. As a result, recovery in these deeper, high-latitude habitats proceeds slowly, and the fossil record from such regions often shows intervals of sparse or absent benthic macrofauna interbedded with layers that record brief episodes of more favourable conditions. Moving toward lower latitudes, the shelves of continents such as Laurentia and Baltica offer a different picture. Many of these regions occupy tropical or subtropical belts, where sea surface temperatures are warmer and seasonal variations in light are less extreme. Here epicontinental seas flood wide interior areas, forming shallow, relatively warm bodies of water that exchange with the open ocean through straits and seaways. In these settings, primary production can be more sustained over the year, especially in areas where nutrient supplies are maintained by river input internal mixing or intermittent upwelling. Phytoplankton communities in the surface waters establish a more continuous presence, with diversity and abundance increasing as the recovery progresses. This in turn supports dense populations of zooplankton and a rich benthic fauna on the seafloor below. Brachiopods, bivalves, echinoderms and other invertebrates can form relatively dense assemblages on soft substrates, while coral and stromatoporoid mounds develop on hard grounds, adding three-dimensional structure to the habitat. These tropical shelves thus often show earlier and more pronounced rebounds in diversity and community complexity than their high-latitude counterparts. They act as centres of diversification, from which lineages can later spread to other regions when conditions permit. Even within a single latitude band, nearshore and offshore zones present contrasting recovery trajectories. In very shallow coastal areas and inner shelf settings, sediment supply from rivers is often high and wave and storm energy can be intense. Substrates here may be unstable with frequent burial and exhumation of the seafloor. Salinity can fluctuate near river mouths, and turbidity may reduce light penetration. Under such conditions, the communities that establish are dominated by species tolerant of disturbance and variability. Burrowing bivalves and worms that can rapidly reoccupy sediments after burial, microbial mats that bind loose grains, when conditions calm, and mobile scavengers that exploit transient food sources are common. Diversity in these nearshore belts may remain lower than in more stable parts of the shelf, but biomass can be high during favourable periods. Slightly farther offshore on middle to outer shelves where sedimentation is more moderate and water depths reduce the direct impact of waves at the bed, except during major storms conditions are more stable. Light still reaches the seafloor in many of these areas, especially where waters are clear, and oxygen levels are often higher and more consistent than in deeper basins. These middle shelf zones support communities with greater structural complexity, including dense assemblages of filter feeders, crinoid meadows in clearer water, and more varied combinations of brachiopods, bivalves and trilobites. It is in such settings that many early Silurian fossil assemblages show relatively rapid diversification and the appearance of new ecological associations. Beyond the outer shelf, break in deeper basinal settings, recovery is more constrained. In basins where deep waters remain poorly ventilated, low oxygen or anoxic conditions persist near the seafloor, limiting colonization by animals. The sediments continue to accumulate mainly through the settling of fine particles and organic matter, with microbial communities carrying out most of the decomposition. Where occasional inflows of oxygenated waters reach the seafloor, they may permit temporary colonization by benthic fauna, leaving thin fossiliferous layers amid thicker packages of barren muds. This pattern leads to a stratigraphic record of alternating stressed and more hospitable intervals, indicating that in the deep ocean, the progression towards stable animal-rich communities lags far behind that on the shelves. Regional tectonic setting further influences the mosaic of recovery. In areas where active convergence builds mountain belts and uplifts coastal terrains, erosion rates and sediment delivery to adjacent basins can be high. Large volumes of siliciclastic sediment may blanket shelves and slopes, creating turbid low-light environments that favour certain kinds of deposit feeders and limit the development of extensive carbonate platforms. In contrast, on tectonically quieter margins with low sediment input, clear waters and stable conditions encourage carbonate production and the growth of skeletal mounds. Their reefs and reef-like communities can become prominent early in the recovery, creating local biodiversity hotspots that contrast with muddier, more homogeneous shelves elsewhere. Semi-enclosed seas and basins, partly isolated by sills or island arcs, contribute additional complexity. In these regions, water exchange with the open ocean may be restricted, making the internal circulation and oxygen budget highly sensitive to the balance between local primary production, evaporation, freshwater input, and occasional inflows of external water masses. Some semi-enclosed basins may experience repeated episodes of strong stratification and bottom water oxygen depletion punctuated by ventilation events. Communities in such basins must cope with these swings, and the resulting fossil assemblages can differ markedly from those of fully open shelves, even at similar depths and latitudes. Differences in recovery pace and style are also seen when comparing various sides of a single continent. For example, one margin may face an open ocean with strong persistent currents and upwelling, bringing cool nutrient-rich waters onto the shelf and supporting high productivity, but also predisposing deeper parts of the margin to oxygen depletion. Another margin of the same landmass may border a more quiescent ocean, with weaker upwelling and clearer, warmer waters, fostering carbonate sedimentation and more extensive reef development. Thus, even within a single tectonic block, the mosaic of habitats and recovery states can be intricate. Over time, as lineages adapt to local conditions and as dispersal connects regions, this patchwork evolves. Tropical centres of diversification send out propagules that can colonize higher latitude or more marginal environments when climatic and oceanographic barriers ease. High-latitude shelves, once they experience longer ice-free seasons and more stable oxygenation, receive these colonists and build communities that, while still distinct, share more elements with low-latitude faunas. Some deep basins gradually become better ventilated as circulation patterns change, opening new spaces for benthic colonization. However, these changes do not erase the evidence of earlier heterogeneity. Differences in community composition and structure between basins, between shelves and slopes, and between climate zones persist, recording the regional paths by which recovery from the first great extinction of complex marine life proceeds. The early Silurian oceans are therefore characterized by a fine-grained spatial pattern in which some areas show advanced diverse ecosystems, while others remain depauperate or intermittently stressed, all coexisting under the same broad global climate trajectory, but responding in locally specific ways to the physical and chemical conditions that define their environments. In the early Silurian oceans, the ability of organisms to disperse, reproduce, and complete their life cycles under changing conditions plays a central role in how recovery unfolds. The extinction has reshaped the physical and chemical environment, and the species that persist or newly arise must operate within these constraints using the biological tools available to them. Across many groups, life cycles now interact with altered currents, habitat distributions, and oxygen patterns, determining which lineages can recolonize emptied areas and which remain confined to refuges or small ranges. Many marine animals reproduce by releasing larvae that spend part of their lives in the plankton. These larvae drift with surface currents, sometimes for days, weeks, or longer, before settling to the seafloor to become juveniles and adults. In the early Silurian, this mode of development gives particular species a strong capacity to spread across flooded shelves and between connected basins. As sea level rises and epicontinental seas expand, new shallow habitats form along the edges of continents and over interior lowlands. Species with planktonic larvae can reach these habitats when currents carry their offspring across sills and along coastlines. The pattern of dispersal depends on the paths of surface currents, the duration of the larval stage, and the timing of spawning, relative to seasonal changes in circulation. In regions where currents flow along the shelf from established refuges into newly flooded areas, larval supply is steady and recolonization can proceed relatively quickly. Where currents run in the opposite direction, or where narrow straits limit passage, larval arrival may be intermittent or rare, slowing the pace of community reassembly. Some organisms rely less on long-lived planktonic larvae and more on direct development or brooding. In these species, juveniles resemble miniatures of the adults and spend little or no time drifting freely in the water column. Their dispersal distances per generation are shorter, often set by adult movement, rather than by drifting stages. After the extinction, such life histories favour persistence and localised recovery in stable refuges, because offspring remain in environments similar to those of their parents. However, they can make it harder for these lineages to colonize distant habitats separated by unsuitable or hostile zones. Islands of diversity dominated by locally dispersing species can form in places where conditions remained relatively favorable through the extinction, while broad, newly accessible shelves may be colonized mainly by species with more dispersive larval stages. The development of resting stages offers another mechanism for resilience. Some planktonic and benthic organisms produce spore cysts or other dormant forms that can survive extended periods of unfavorable conditions. These resting stages may settle into sediments or remain suspended in the water column, with metabolism reduced until temperature, oxygen, or nutrient levels become suitable again. In basins where oxygen levels fluctuate, or where seasonal extremes are strong, such stages allow populations to bridge intervals during which active life would be difficult. When conditions improve, germination or reactivation of these resting forms can seed rapid local population growth without requiring new immigrants from elsewhere. In this way, life cycles with built-in dormancy contribute to the persistence of lineages across environmental swings during the recovery phase. Reproductive output and strategy also influence the pace of recolonization. Species that produce large numbers of small offspring can, under favorable conditions, expand their populations quickly and spread widely. Their larvae or propagules may saturate local currents, increasing the likelihood that some will reach new habitats. However, high offspring numbers often come at the cost of lower parental investment in each individual, making survival more sensitive to environmental conditions. In contrast, species that produce fewer larger offspring may confer greater reserves or better developmental prospects to each juvenile, potentially increasing survival where conditions are challenging but reducing the speed of population expansion. In the early Silurian, both kinds of strategies can be seen in the fossil record through patterns of shell-sized distributions, growth rings and population structures, although many details remain inferred from comparison with later relatives. The interplay between sexual and asexual reproduction shapes genetic variation and adaptability. Most complex animals and many algae reproduce sexually combining genetic material from different individuals to generate offspring with new combinations of traits. This shuffling of genetic information allows populations to explore a wider range of potential responses to their environment and to retain combinations that confer higher fitness under the altered conditions following the extinction. Some groups also retain the capacity for clonal or asexual reproduction, budding or fragmenting to produce genetically identical copies. Asexual reproduction can be advantageous for rapid local expansion in a stable habitat, but offers less flexibility when conditions change. In early Silurian communities, lineages that maintain effective sexual reproduction and sufficient population sizes are better placed to respond to shifting oxygen boundaries, nutrient regimes and habitat configurations over the course of the recovery. Developmental constraints place limits on how far and how fast life cycles can change. The body plans of major animal groups are established long before the end Ordovician extinction, and their basic developmental pathways persist into the Silurian. Brachiopods, for example, still pass through larval stages with characteristic features before settling and secreting adult shells. Crinoids continue to grow from free-swimming larvae into stalked juveniles anchored to the substrate. These developmental programs constrain the range of life history modifications that are readily accessible in the short term. Evolutionary change in larval duration timing of metamorphosis and reproductive timing is possible, but wholesale shifts between fundamentally different developmental modes are less likely over the timescales of the early recovery. As a result, the post-extinction distribution of life histories reflects both the selective winnowing imposed by the crisis and the inherent flexibility of existing developmental systems. Physiological tolerances and plastic responses further shape resilience. Species differ in their ability to withstand low oxygen temperature fluctuations and variations in salinity. Some can adjust their metabolism behavior or microhabitat use within a single lifetime. For instance, animals capable of reducing activity during episodes of mild oxygen depletion can persist on the margins of low oxygen zones, exploiting habitats that are inaccessible to more sensitive competitors. Organisms that can shift their vertical or horizontal position in the water column, or the sediment in response to changing conditions, may maintain suitable microenvironments, even as broader environmental parameters fluctuate. Such plasticity does not remove the need for genetic adaptation, but it can buy time and space for populations to endure recurrent stress during the recovery interval. Ecological interactions woven into life cycles also contribute to resilience. Mutualistic relationships between framework-building corals or stromatoporoids and their photosynthetic partners depend on light water clarity and stable chemistry. Where these conditions are met again after the extinction, the mutualism allows skeletal builders to grow more rapidly and to invest in three-dimensional structures that provide habitat for other species. Symbiotic associations between invertebrates and microbes that assist in nutrient acquisition, detoxification, or other functions also help some hosts to tolerate marginal environments, such as sediments with fluctuating oxygen or high concentrations of reduced chemicals. Predator-prey interactions influence which life history strategies are favoured. Where predation pressure is high on larvae or juveniles' life cycles that shorten vulnerable stages or place them in less exposed environments are advantageous. In environments where predators are sparse during the early recovery, longer larval durations or more exposed juvenile stages may be less costly, allowing species to take fuller advantage of dispersive larvae or extensive grazing on open surfaces. Over time, as predator communities rebuild, these selective pressures shift, and life cycles may adjust accordingly, though again within the bounds set by developmental and physiological constraints. The spatial structure of populations, often described as metapopulation dynamics, becomes important in the patchy recovering seascape. Suitable habitats for a given species may be scattered across a shelf or across multiple basins separated by less favourable areas. Local populations can go extinct through random events, environmental fluctuations or competition, but they can be re-established if propagules arrive from other occupied patches. The balance between local extinctions and recolonizations depends on dispersal potential reproductive rates and the connectivity imposed by currents and geography. In the early Silurian, this level of population turnover contributes to the observed pattern of communities that appear and disappear in the rock record across relatively short vertical intervals, even when global conditions are trending toward greater stability. At the level of lineages, resilience arises from a combination of these mechanisms. Species that survived the initial extinction pulses often share traits that allowed persistence through environmental extremes, such as broad tolerance ranges, flexible life histories, or the capacity to inhabit refuges with more stable conditions. During the recovery, these same traits facilitate expansion into new or returning habitats. New species that originate from surviving lineages inherit many of these characteristics, though they may refine them in specific directions as they adapt to particular niches. The result is that early Silurian communities, while taxonomically distinct from their Ordovician predecessors, carry a strong imprint of the biological mechanisms that underpinned survival during the crisis. In combination with the physical rearrangement of habitats and the evolving chemical environment, these life cycle traits, dispersal capacities, and developmental constraints determine which branches of the tree of life continue to spread across the reflooded shelves and into the reorganized water masses of the early Silurian oceans, providing the internal machinery that allows recovery to proceed under the external conditions already in place. In the early Silurian oceans, as communities re-establish on shelves, slopes, and in the open water, ecological interactions among organisms begin to reorganize the structure of ecosystems. The same basic processes that have long shaped marine life competition, predation, facilitation, and symbiosis continue to operate, but they do so among a modified cast of species and within habitats redefined by glaciation, sea level rise, and shifting oxygen patterns. In this setting, the ways in which organisms divide resources, avoid or confront predators, and use each other as habitat or partners create new configurations of niches, many of which differ from those that prevailed before the end Ordovician extinction. On the seafloor of shallow shelves, competition for space and food plays a central role, where environmental conditions are favourable enough to allow dense communities. Brachiopods, bivalves, bryozoans, echinoderms, and other sessile or slow-moving invertebrates share the upper layers of soft sediment and the surfaces of hard grounds and skeletal mounds. Each group filters particles from the water column or processes organic material in different ways, but their feeding zones overlap. Where currents are strong and particle flux is high, many suspension feeders can coexist with limited direct interference, each drawing on the continuous supply of plankton and detritus. In more moderate or low flux settings, however, spatial crowding and overlapping filtration volumes can lead to competitive exclusion. Species that can elevate themselves slightly above the sediment, either by stalks, tall shells, or attachment to raised substrates, gain access to faster flowing water and a greater delivery of particles. Those that remain close to the bed must feed from slower boundary layers and may be disadvantaged when densities increase. Over time, these differences in feeding height and attachment strategy produce a vertical layering of filter feeders, sometimes described as ecological tiering, in which species partition the near bottom water column. Similar tiering occurs within the sediment. In faunal animals such as burrowing bivalves, worms and other soft-bodied invertebrates occupy different depths in the substrate. Some live just beneath the surface, reworking the upper centimetres of sediment and feeding on freshly settled organic matter. Others construct deeper burrows and tubes, accessing older deposits and more stable chemical conditions. Their activities mix sediment, bring oxygenated water downward, and alter the distribution of organic material and reduce compounds. By occupying different vertical zones, these in fauna reduce direct competition and create a gradient of conditions that other organisms can exploit, from oxygen-rich upper layers to more reduced deeper sediments. Predation exerts another organizing influence. On the seafloor, eurypterids, large arthropods, and early nautiloid cephalopods move across or above the bottom, feeding on trilobites, brachiopods, worms and other invertebrates. Evidence from damaged shells and trace fossils suggests that gyrophagus feeding in which predators crush or break hard parts is already significant in some Silurian communities. In response, some prey lineages display thicker shell spines or enrollment behaviors that increase protection, while others adopt strategies of rapid burrowing or nocturnal activity patterns. Mobile predators also affect where their prey can live. In areas frequented by large eurypterids, for example, shallow waters may be less favourable for exposed epifaunal organisms, encouraging them to occupy deeper habitats, cryptic microhabitats under shells or within mounds, or to develop behaviours that reduce encounter rates. In the water column, predation shapes planktonic and nectonic assemblages. Jawless fishes feed on small prey and organic particles, while larger vertebrates and arthropods prey on them in turn. As early jawed fishes begin to appear and diversify during the Silurian, they introduce new modes of feeding. Simple jaws and associated musculature allow more efficient grasping, biting, and processing of prey than the suction-based or filter-based methods used by many jawless forms. Even if jawed fishes are not yet abundant everywhere, their presence in some basins alters predator-prey dynamics. Prey species in those regions encounter new sources of mortality that may favour increased mobility, schooling behaviour, or the occupation of refugees in complex habitats. Jawed fishes themselves can explore new dietary niches, including more active predation on larger invertebrates and vertebrates, broadening the range of trophic roles available in the recovering ecosystems. Symbiotic relationships contribute to ecological innovation and stability. On carbonate mounds and reef-like structures, corals and stromatoporoids often associate with photosynthetic partners that enhance their energy budget and growth. This partnership allows them to build skeletons more rapidly in clear, shallow waters, expanding the three-dimensional structure of the habitat. The resulting frameworks offer surfaces for encrusting organisms, crevices for shelter, and perches for suspension feeders. In some cases, encrusting bryozoans and other colonial organisms form a secondary layer over coral and stromatoporoid skeletons, further increasing structural complexity and surface area. These assemblages illustrate how mutualistic interactions can amplify the effects of primary production and physically reshape the sea floor at local scales. Facilitation extends beyond direct symbiosis. Burrowing animals oxygenate sediments and modify their physical properties, making them more habitable for other species that depend on well-mixed substrates. Epifaunal organisms provide hard surfaces for smaller encrusters and epibionts, including small sponge-like forms and tube-dwelling worms. When skeletal mounds grow, they locally alter flow fields, enhancing food delivery to filter feeders and creating sheltered areas where weak swimmers or delicate larvae can settle and survive. The indirect effects mean that the presence of a particular group can expand the range of conditions under which other groups can exist, supporting more diverse and intricate communities than would be possible in their absence. Competition for light and access to water movement is evident among photosynthetic and filter-feeding organisms in shallow settings. Microbial mats, filamentous algae and small macroalgae can carpet sediment surfaces and hard substrates, intercepting light and stabilizing sediment. Filter feeders that attach to these surfaces may shade or overgrow their phototrophic neighbors, while the mats themselves can impede settlement by larvae that require bare substrate. Over time, alternating phases of mat dominance and animal colonization can occur, driven by changes in sedimentation rates, disturbance events and nutrient levels. In some areas, stable, clear waters favor sustained growth of skeletal frameworks and attached fauna, whereas in others, periodic sediment input or low oxygen episodes allow microbial communities to reclaim surfaces. Ecological interactions also influence how communities respond to recurring environmental stresses during the recovery. In regions where low oxygen waters periodically intrude onto the shelf, tolerant species such as certain bivalves and worms may persist and dominate between episodes, while more sensitive taxa retreat to shallower or more oxygenated areas. When oxygen levels improve, colonists from refugees or from surviving local populations recolonize the affected zone, but the identity of the first colonizers, often opportunistic generalists, can shape the trajectory of succession. Their presence can either facilitate or hinder the establishment of later arriving species by modifying substrates and resources. In some cases, repeated disturbances lead to communities maintained in an early successional state dominated by fast-growing tolerant species, while in more stable areas, competitive interactions and niche partitioning allow more complex assemblages to develop. As early jawed vertebrates expand their interactions with invertebrate prey, and with jawless fishes set the stage for longer-term evolutionary trends. Efficient biting and processing of prey can increase the overall pressure on shelly and soft-bodied organisms, reinforcing selective regimes that favor defensive traits, such as thicker shells, spines, or cryptic habits. With invertebrate assemblages, competition for food and space may promote differentiation of feeding strategies and habitat use. Some jawed fishes may specialize on planktonic prey in midwater, others on benthic invertebrates, and still others on larger nectonic animals. Such diversification partitions the available prey spectrum and reduces direct overlap. The early steps of this process in the Silurian contribute to a more complex set of vertebrate roles, even though the full expansion of jawed vertebrates lies in later periods. In planktonic systems, both competition and facilitation occur among primary producers and grazers. Different phytoplankton lineages may compete for nutrients and light, with small, fast-growing forms dominating under conditions of frequent disturbance and variable nutrient input, and larger, slower-growing types becoming more common in stable nutrient-rich layers. Grazers exert selective pressures on phytoplankton size, shape, and defensive traits. In turn, the structure of the phytoplankton community influences the efficiency of energy transfer up the food web and the fraction of organic matter exported to depth. Microbial loops in which dissolved organic matter released by primary producers and consumers is taken up by bacteria and then returned to the particulate food web through protozoan grazers add further complexity, linking what might otherwise be lost energy back into higher trophic levels. The balance of these interactions shapes how much carbon and nutrients remain in surface waters versus how much is transported to the deep ocean. Across these various environments, emerging innovations in ecological relationships do not involve completely new processes, but new combinations and intensities of familiar ones. The distribution of roles among species has changed because some groups are absent, others have contracted or expanded their ranges, and new taxa have appeared. Ecological networks in the early Silurian thus exhibit different patterns of dominance of who eats whom, and of who constructs or modifies habitat compared with their Ordovician predecessors. The rebuilding of these networks through countless individual interactions of competition, predation, mutualism, and facilitation determines how stable and resilient communities become under the post-extinction conditions and how energy and materials flow through the recovering marine ecosystems from the surface waters, where light is captured to the deeper settings, where organic matter is ultimately recycled or buried. The story of recovery from the first mass extinction of complex marine life is known not from direct observation, but from the rocks and fossils that record conditions in the Ordovician and Silurian. On flooded shelves in deep basins and along ancient coastlines, layers of sediment accumulate during and after the extinction interval, preserving a partial record of organisms, sediments, and chemical conditions. When these deposits are later uplifted and exposed, their textures, fossils, and geochemical signatures allow reconstruction of how the oceans move from crisis into a new stable state. At the scale of hand specimens and thin sections, the most direct evidence for recovering life comes from fossil assemblages. Beds of limestone and shale record shifts in the presence and abundance of taxa through vertical successions. Late Ordovician layers that contain diverse brachiopods, trilobites, corals, and other invertebrates are overlain by thinner, less diverse assemblages or by intervals with very few body fossils near the extinction horizon. Above these early Silurian strata show the reappearance of some surviving lineages, the introduction of new species, and a gradual increase in fossil richness and disparity as time progresses. In some sections, brachiopod faunas change from diverse fine-scaled communities with many coexisting species to simpler assemblages dominated by a few tolerant forms, and then back toward richer, more differentiated communities. The timing and style of these transitions differ between basins, but together indicate that community reassembly proceeds in steps, with early colonists occupying stressed environments, and later arrivals filling a broader range of niches as conditions become more stable. Microfossils offer another window into the recovering biosphere. Organic walled microplankton such as acritarchs and the remains of planktonic organisms like graptolites occur in fine-grained sediments deposited in offshore and basinal settings. Their diversity patterns across the Ordovician-Silurian boundary show significant reductions near the extinction interval and renewed diversification afterward. Because these organisms are widespread and their evolutionary changes are relatively rapid on geological timescales, they serve as biostratigraphic markers that allow correlation of sections separated by thousands of kilometers. By comparing graptolite and acritarch successions in different regions, it is possible to infer where planktonic communities recover quickly and where they remain depauperate for longer intervals. Trace fossils add information where body fossils are sparse. Burrows feeding trails and other sedimentary structures produced by the activity of animals record the presence of benthic communities, even when shells or skeletons are rare or poorly preserved. In some successions, intervals of laminated, undisturbed muds near the extinction interval suggest times when few benthic animals lived on or in the sediment, consistent with low oxygen conditions or severe ecological stress. Overlying layers show increasing abundance and complexity of trace fossils with shallow burrows, giving way to deeper, more intricate structures as infaunal communities re-establish and diversify. These changes in bioturbation affect the physical properties of the sediment blending layers and altering the way organic matter and redox-sensitive elements are distributed. Sedimentary features independent of fossils also constrain environmental conditions during recovery. Grain size trends, the presence of graded beds, and the geometry of facies belts in ancient shelf and slope deposits record sea level changes in the shifting positions of shorelines, deltas, and carbonate platforms. Stacked packages of shallow marine and deeper water faces trace the transgression of the sea across continental interiors, and the subsequent stabilization of epicontinental seas. The thickness and composition of organic rich layers, nodular limestones and iron-rich beds provide clues to periods of low oxygen high productivity or changes in sediment supply. These physical records tie the biological patterns observed in fossil assemblages to regional and global changes in sea level climate and basin geometry. Geochemical proxies extend the record beyond what is visible at the scale of grains and fossils. Ratios of stable isotopes, particularly carbon isotopes in carbonate minerals, and organic matter vary through time in response to changes in the global carbon cycle. A carbon isotope excursion near the Ordovician-Silurian boundary reflects shifts in the relative burial of organic versus inorganic carbon during and after the extinction. In the early Silurian, the gradual return of carbon isotope values toward more typical levels indicates a move away from the extreme conditions that characterized the crisis interval. The fine structure and regional expression of these isotopic trends help to constrain the pacing of environmental change and the timing of recovery in different parts of the world. Other isotope systems and elemental ratios provide information on redox conditions and nutrient cycling. Variations in sulfur isotopes and in the relative abundance of redox-sensitive trace metals such as molybdenum or uranium in organic-rich shales signal the extent and intensity of low oxygen and euxinic conditions in ancient basins. Iron speciation assessed through the relative proportions of different iron-bearing minerals can distinguish sediments deposited under well-oxygenated low oxygen and persistently anoxic bottom waters. In sections that span the end Ordovician extinction and into the Silurian, these proxies show that anoxia expands in some basins during the crisis and then contracts or becomes more localized afterward, though with superimposed fluctuations. Combining such geochemical data with fossil and sedimentological evidence allows a more complete picture of where and when the seafloor becomes suitable again for diverse benthic communities. The rock record also contains signals of temperature and ice volume that frame the recovery. Oxygen isotope ratios in conodont apatite and other skeletal materials vary with seawater temperature and global ice volume at the time of formation. Higher ratios in late Ordovician intervals reflect cooler conditions and larger ice sheets, while lower ratios in early Silurian samples indicate a shift toward warmer climates and reduced ice. These trends are not uniform in all regions, in part because local environmental factors such as salinity and water mass structure can influence isotope values. Nonetheless, when integrated with sedimentary indicators of glaciation and sea level, they support the view that the early Silurian marks a move into a less extreme climate state, one in which recovery is possible, but still modulated by residual cool conditions in some regions. The resolution of these records is limited by several factors. Sedimentary layers integrate processes over timescales ranging from individual events to thousands of years, and fossil assemblages in any given bed are time-averaged composites of organisms that may not have lived together simultaneously. Erosion and non-deposition remove parts of the record entirely, creating gaps that must be inferred rather than observed directly. Diagenesis, the suite of physical and chemical changes that sediments undergo after burial, can alter original mineralogical and isotopic signals. In some carbonates and shales, later fluids overprint the primary geochemical signatures, complicating interpretation. Sampling biases also influence the apparent patterns of recovery. Well-exposed sections are not evenly distributed across paleogeographic settings, and the preservation potential of certain environments such as high-energy shorelines or some deep basins is lower than others. As a result, the fossil and geochemical records are richer in some regions and habitats than in others, which can give a skewed impression of global trends if not carefully assessed. Despite these limitations, consistent patterns emerge when multiple lines of evidence are compared. Fossil assemblages in many basins show an initial drop in diversity and ecological complexity at or near the extinction horizon. followed by a stepwise increase through the early Silurian. Trace fossils document the return of burrowing and sediment mixing, while sedimentary facies changes track the flooding of shelves and the establishment of new shallow seas. Carbon, sulfur, and oxygen isotope trends, together with redox-sensitive element distributions, record shifts in the carbon cycle oxygenation state and climate that accompany and frame biological recovery. The rock record does not capture every detail of this process, and it cannot resolve events on the shortest timescales, but it preserves enough information to show that the rebuilding of life after the first mass extinction is neither instantaneous nor uniform. Rather, it is a multi-stage process recorded in layers of mud, sand, carbonate, and fossil remains in which physical, chemical, and biological signals together document how the oceans move from crisis into a new configuration of climate circulation habitats and ecological networks.